All right, hello world. This is CS50 Live, where we do all kinds of things. We program things from scratch, look at technical concepts. We looked at Kali Linux last week, and that was super exciting. It feels like it was quite a long time ago. My name is Colton and Nick. This is CS50's Nick Wong.
Hello.
Nick, what are we talking about today?
Yeah, so today, I think as advertised, we're talking about images and machine learning and classifying, some of the three key buzzwords that are thrown out there. Images is kind of a fun non-buzzword, but machine learning's out there, classification. We'll actually be doing a little bit of unsupervised learning as opposed to supervised, and things like that. I think previously on the stream we talked about a binary classifier that could tell you if something was I think a cartoon.
That was your first.
Oh, that was the very first one.
Your very first stream that you did with us, actually.
That was a long time ago.
Probably episode 4 or 5.
Yeah.
Maybe earlier.
Time out there. I see the gongle joke is back on the. And people actually put up a website for that. That's fantastic.
Somebody asked if we're going to have captions for this video, and we are in the process of captioning all of our streams, actually. So this one will have captions eventually, maybe within a couple of weeks or so. And shout out to all the people that are currently in the chat. Much appreciated. Chat's very poppin'.
Yeah, wait, does that mean they're going to caption my incessant laughing?
Yeah,
or is that
I was going to say, it's just, we're going to grep laugh, and there's going to be 8,000 lines.
Oh, man.
Your shirt, by the way, is very ethereal.
Thank you. Yeah, I feel very light today. You know, it's kind of a nice-ish day. There's a really nice day on Sunday. That was awesome.
Oh, true.
Yeah,
Recently, it's been very warm. It's going to be 70 in Massachusetts. Freezing here, by the way, normally.
What I want.
Yeah. But sorry to take away from that.
Yeah, no, it's all good. It's just beautiful.
So we talked about classification. That ties into sort of what we're doing.
Right. So we classified kind of between two just different groups that were completely non-intersectional. And now we are trying to, given a set of data, can we figure out how many classes there should be, more or less?
Is this sort of alluding to, we sort of publicized Kmeans Clustering?
Yes. So Kmeans, for those who are kind of unfamiliar with the term, it's a form of unsupervised machine learning. Unsupervised meaning I don't tell it what the right answer is. It just figures out what its guess as to the right answer is. And in this case, that manifests itself as there are K clusters, if you will, of data. And so let's say I have my entire data set, and actually, we'll just talk about the data set we'll use today, which is, I think, around 40 or 50 images. So really not that much data. But it is 40 or 50 images, and there are, I think, 4 or 5 classes. And those 4 or 5 classes are the different streams that we've done that had the same little box.
So you took multiple screenshots of one stream?
Throughout one stream. So within each cluster, there should be around 10 images, and those 10 images should be all from the same stream. So essentially what our classifier will want to do, what a Kmeans classifier will do, is it says, OK, I have this large data set, and I'm going to just grab a bunch of random pieces from the data set, and those will be my initial clusters. So the initial means are pretty random. They're all roughly the same-ish. It depends on the distribution of your data, but they're pretty reasonable. So we just kind of grab some random images, throw them into a cluster, and we say, all right, now tell me which image or I guess actually for each image, which cluster is that image closest to by some definition of distance. So on the stream today, we'll probably use Euclidean distance. It's pretty common. It's really easy for everyone to know.
This is geometrical x, y.
I just do x minus x naught squared plus y minus y naught squared, and then I take the square root of those sums, those sum together. And that works in many
dimensions. It's the distance formula, right? The linear distance formula.
It's your favorite, was it 7th grade concept?
It's used for
it comes back all the time.
Spherical collision detection. That's often used.
Yeah, it's used actually a lot in game development.
It would be cyclical, not spherical.
Yeah, but same concept. And so we'll basically be doing that. And every iteration of the algorithm, it says, hey, for each image, what cluster are you closest to? And then I'm going to stick you in that cluster. And once you're in that cluster, I'm then going to recompute the new mean of the cluster. And so things that were kind of naturally closer to some set of images, they're going to end up kind of clustering themselves. And those means will get closer to the images that are all in that cluster as you iterate over the algorithm. One of the benefits of K-means clustering is it actually doesn't take that many iterative steps. You can usually do it in a couple, like 10 or so. So you really just kind of iterate over it, on the order of 10 times. And after that, your loss doesn't really get any better. You tend to stick around, it depends on your situation, it depends on the way you've built it and kind of the randomization parameters you have in there. But in general, you don't need that many iterations to get a pretty accurate representation of what things look like. One of the kind of cool parts of K-means is I have this kind of center of a cluster, and so I would generally just refer to that as the mean image for that cluster. And those mean images are often representative of what is in that cluster. So let's say one cluster is from our Kali Linux stream, then if I take whatever the mean or the center of that cluster is, it should be pretty representative of what we on average looked like in that stream. Now, we haven't tested these, right? So we're pretty sure that it'll work reasonably well, but we leave ourselves a little untested to kind of verify that things are kind of funny, and it gives you guys some room to experiment, I guess, and we get to experiment and show you guys cool things. So you will see some kind of entertaining stuff with our Kmeans clustering, but our prediction is roughly that you should see what we looked like on average on a given stream, and given a new image, it'll tell us which cluster it should have belonged to, and it'll then classify for us.
Do we usually manually choose the start of the cluster, or do we just kind of randomly, or how do we get to the beginning of that?
So that's a great question. A lot of times we actually initialize it with just completely random beginnings. So we just say, hey, here's my data set. I'm going to use like a NumPy application to randomly pick some set of images or randomly subdivide the images into these clusters. So our initial can be random. But there is another version of this that is called semi-supervised learning. So let's say you were able to label about half of your data before your research intern quit. And by you labeled your data, I mean your intern labeled half of your data and then they quit. So you have this data set of 1 million images, and 500,000 of them have been labeled manually by some poor college student, and the other 500,000 have not been labeled. So this is where, if everything was labeled originally, if all 1 million images have been labeled, then we would call that supervised learning because we know the answer. And then we have some test data set or some prediction kind of way of accumulating things that we want to predict upon, and those are unlabeled, but we're going to use our trained model to then predict on those. Now, in semi-supervised learning, we have this, where maybe half our data is labeled and half of it is not. And so we take maybe the half that's labeled and we assign them to the right clusters. So this is where we actually start with all of this cluster, we know this is the right class. All of this cluster is all in the right class, and so on. But the other 500,000 images, we don't know which cluster they belong to. So we'll then iterate this algorithm over those images and say, hey, which cluster are you closest to? And so that can be a way of tightening up what your Kmeans classifier will actually do. But it gives it more data, which allows it to spread over different kinds of variants or whatever the underlying distribution of those things are.
SGGST04 was saying even the second guy seems bored. No, we had a bug with our Facebook deployment, so I was just focused on getting us streamed to Facebook, which we now are. I guess as we were initially publishing this, OBS sort of bugged out and caused the Facebook stream to crap out.
No.
So no, I was sorry. I was zoomed in on getting that focus. But he or she asked another question earlier, which was, where was it? I'm proficient in Python, but know nothing about ML AI. Is this stream for me? What do you have to say about that?
Yeah, I think this is a very reasonable stream. Even if you're not super great in Python, or if you're very adequate, I would count myself as decent in Python. This would still be pretty reasonable for you. So our goal is to kind of, at the beginning, we're going to do this kind of high-level approach, what are we going to go through, what are kind of the concepts, but then we're going to repeat those concepts pretty much throughout the stream so that you really get a sense of what we're actually talking about. So for instance, if you're really you want to do this yourself, then you can code along. We should be going at a reasonable speed. You can also always pause the video, go back, reiterate. And that should be easy for you if that's how you learn. If you learn through listening to what we say, then maybe a different iteration will help you. If this one doesn't work, if this makes perfect sense to you, then that's great. There are many different ways that we're going to try and attack this same problem. And I saw somebody said, please also talk about limitations of Kmeans clustering, as in if there are two concentric circle kinds of data, then your Kmeans clustering might have some problems with identifying which one is which. So for example, let's say I have some data set and then I have some other data set that is a subset of the original data set. This clustering method doesn't really work super well for classifying between those two data sets, right? So let's say I wanted to classify between all kinds of dog versus poodles, for example.
Right.
It might be a little bit tricky for me, and actually that might not be the best example, but it's kind of the idea, which is that I have this subset of the data that I want to kind of classify as separate from the rest of the data, and that can be really difficult for Kmeans. Because Kmeans, by definition, is really just looking at what mean image can I get out of some data set, and how can I find things that are closest to that mean by some measure of distance. And so for something that has kind of, on average, the mean image of the entire data set is very, very close to the mean image of the subset data set, then Kmeans can't distinguish the two, but maybe you could look at other feature discrimination algorithms. So
it's a deep field.
Yeah, there's a lot of things to do.
A lot of complexity. It's very interesting, but I'm very excited to learn, I think, a little bit more about it. I'm gonna transition to your laptop view.
Yeah, no worries.
Just to make sure I can see everything that's going on here.
And while you're doing that, at the very end of the stream, we will hopefully have a little bit of time to kind of sneak peek what we'll go into next week, which is using an actual neural net to not only classify images and understand like which parts go where, but also generate new ones based on what it knows. And that's what we call a generative model.
Oh, sure. And then potentially into generative adversarial networks,
yes,
too.
And eventually we will hopefully get, or I guess not eventually, after maybe that, we will hop into generative adversarial networks.
So this won't be just a single part stream. This will happen over the course of many parts. But yeah, I think it'll help people to get a groundwork understanding of a lot of the pieces.
Yeah, and so I think that it's a very good point to recognize that there are limitations to this, that the next stream will kind of cover why there aren't necessarily as many.
So this is a beautiful screensaver we have for the folks that are brand new.
Right. This is C matrix. I piped it, so on OS X, I piped it through lolcat. Lolcat rainbowifies things. C matrix makes things, it makes kind of like a matrix style screensaver. I'm a huge fan of using it. I don't know who created it, but I guess we're kind of doing free advertising for them. They're really cool. It's a cool project. I'm a huge fan of using it. I think it looks techy and
if anybody wants to look like they're a true sort of sci-fi fantasy hacker.
You don't even have to code. You just leave that on there and people think you code, you know?
So what is the first step, I guess, in the actual coding of today? What are we going to look at first?
Right. So, you know what? Let's actually look at our data set. Just because I think that would be
image. That image is cool, too.
Thank you. Actually, these are all from Unsplash. All of my desktop images are Unsplash.
I recently just used I'm learning React, and we use the Unsplash API.
Yeah. Their API is really nice. It's super well built.
Very, very clean API.
So we have this kind of 4 classes of, and maybe I can make this bigger. Nope, can't.
Is that a Ruby or, for an important question, is that a Ruby or a Snapple?
This is a Snapple. So we're also advertising for Snapple. This is Raspberry Tea. I pretty much every stream grab a Snapple because a lot of times I'm running over here. And it helps me sound a little less awful.
You get parched and just a tiny little bit of caffeine.
Yeah, exactly. And then just nice. Like, it's, you know, oh, yeah, we're going. In case I'm not energetic enough, I'm not really going. Yeah, I also do love root beer, but I'm trying to avoid drinking too many sodas.
Respect.
So, yeah,
respect.
As a kind of interesting tangent to your Kmeans classifier intro. So we have these 4 different classifications of data. Sorry, I thought there might have been 5. There are only 4. I've just basically.
Well, there's the all. I don't know.
Yeah, there is all. It is unfortunately not a separate class.
It'd be like an umbrella cluster, I guess.
Yeah, it's kind of like everything.
It's just like a big circle.
And so we know the answers, but we're not going to use the answers, so to speak. We're going to do fully unsupervised learning to start. But if you kind of look through some of these images, they're literal.
Man. I look burnt.
We look. Yeah, we're chilling.
Completely burnt.
Oh, whoops, that's not what I wanted to do. Yeah, we look great in every image. I unfortunately did not have the foresight to select for appealing images, but there are images of us, and so you do have many different images pulled throughout a stream. And
it's the same. I noticed it's the exact same dimensions too.
Yes, yeah. So I normalized across dimensions to make our lives a little easier, but I didn't normalize across how much of the frame we occupy.
Sure.
So I did very minimal pre-processing in that I literally only just made sure they were the same size.
Right.
They're the same size, the same like pixel quality. So we have the same resolution on all of them. But other than that, nothing else was done too crazily. Now these first 2 are fairly easy to distinguish. We're wearing very different colored shirts. And we're in other positions. However, these last 2, you'll notice that we're both wearing black.
Oh, wow.
And the background is not particularly easy to discriminate against.
Yeah.
So we kind of picked 2 things that are pretty easy. They'll be standout kind of outliers almost. Their means should be pretty different. These ones, their means don't look that different. Now we move around a lot, and how means translate as far as like machines are concerned is a little different. But you'll notice that the CTF stream and our Kali stream, we were both wearing black. With the exception of the white.
We're going to operate off of the sheen of my forehead.
Yeah, it might literally be that. And your glasses.
In that stream, yeah, the glasses.
For human beings, there's Colton has glasses. There's a very shiny quality to, I think, both of our foreheads in the one. And I have a logo on my shirt that definitely helps.
The hair is pretty distinct, I suppose. And today it looks like trash, by the way.
No, you're fine.
I appreciate that. It's like all over the place.
Everyone has those days, and you're still chilling.
you gotta chug through it, you know. Oh, and,
exactly.
Not ask any suggestions on books about ML.
Oh, that's a good question. So there is, what is the name of that book? I have a textbook on my desktop somewhere that I really like. It is called now you're going to see all of my other weird things. So there's this Bishop Pattern Recognition and Machine Learning Springer 2006 textbook. I have a PDF version of it, but I think that that's a pretty great book for kind of going through. It requires a decent amount of math background and like stats background. But if you're comfortable with like what a CDF is, how to convert between CDFs, PDFs, what like standard CDFs and PDFs might look like, how to like go through different distributions, how some basic linear algebra concepts work, so kind of like different matrix operations. If you're familiar with like the Matrix Cookbook by MIT, then this book is probably pretty useful for you. If that all sounded really esoteric, then that's fine. I would go online and kind of look at some kind of basic tutorials. Medium is a good place to start with like some very simple tutorials, kind of like what we're going to do right now. Wow, the internet's amazing. You guys just found that so quickly. So there's those places. Adamantine Bipartite says try scholarly articles for ML, Google Scholar. That's definitely a great place to start. Be aware that there is a lot of terminology and symbolism that might, or notation really, that can be really intimidating at first. I wouldn't try not to be intimidated by them. They just take time. But I would definitely recommend kind of like looking through what things are out there. There's all sorts of cool papers all the time on different things. And then a lot of times there's articles about those papers that are even easier to read. So kind of, go as you will.
And I realized Curious King was asking, so what do you guys do? We didn't really talk about that for any of our new viewers. Yeah. CS50 is Harvard's Intro to Computer Science. It's taught by David Malin, who's not present here in this stream physically, but might pop in a little bit later. Yep. My name is Colton Ogden. I work as a full-time technologist, and I also do this Twitch streaming and a bunch of other stuff, programming, other related things. Nick?
And then I actually was on CS50 staff for 2 years or so, and that's how I ended up working with these guys. And then the rest of my time is spent being a student. I'm just a full-time student.
Remind me of what you're. I don't remember 100% if you were doing CS as your concentration,
right? Or
if you're doing biomedical engineering.
Yeah. So my major, I actually have a joint or double major in bioengineering and computer science.
Okay. Well, so that's why I wasn't sure.
Yeah.
Because it's literally
it
both
is very
of those
difficult
things.
to remember which one. And so I'm doing both. And most of my time is spent studying. I think if I didn't have to spend all of my time doing just P-sets constantly, problem sets, for those who aren't familiar, then I would probably produce much more high-quality preparation on these streams. But that's okay. I think it's still pretty entertaining.
This will be fun.
It'll be fun.
And you've taken an ML course here?
Yeah, and I'm also currently in our ML course, actually.
Okay.
So I've actually taken mostly systems courses. So I focus a lot on like systems. I really like data visualization, but I haven't gotten the chance to take a course in it. I've really focused on systems. So I'm fairly familiar with systems. If you want a really bad version of my C programming, you can go watch our C programming stream. The point of that stream was not my C programming, but we did end up kind of going through some C programming. It's pretty bad, but at least that way you get to see me code very poorly if you think that this is really good. If you think this is really poor, don't go look at that. You'll probably cry. But I really don't know where. I think I just kind of got interested in ML as actually in CS50. I was kind of like, oh, machine learning seems really cool. My TF was kind of like, yeah, you should go for it, And I tried some very high-level libraries. I didn't have to understand much about the theory, and kind of from there, I hopped into a bunch of articles and I started building little examples myself. And then I think I built like a small room camera that, upon someone from my family entering my room, it kind of like identifies who they are and notifies me. It's kind of just for fun. A lot of times you just build projects, and as you go, things kind of pop out of the woodwork. But yeah.
The Erosity asked an interesting question, which was, do you have any hot takes on whether the hype for Golang in the future of ML is justified, just beginning to learn the language? And you're going to go work for Google.
I am, yeah. So it's kind of an appropriate question. I actually really like Golang, and I'm not super familiar with it yet, but I do intend on becoming like that, on becoming much more familiar with it. So Golang, language invented by Google, sometimes referred to as just Go, not to be confused with the board game. And Golang is a very interesting language in that it still allows you to have access to low-level things. C++ style, C style. I can still touch memory and access primitives. But it has a much nicer, well, a lot of people believe, and this will set off a firestorm somewhere, but many people believe that it has a much nicer interface, kind of a la like Python or JavaScript, than do like C++ and C.
It also has a garbage collector, doesn't it?
It does. It has a very nice garbage collector. So for those of you who aren't familiar, garbage collection is something that's really popular in like Java, for example. Well, really any like modern-ish language, with the exception of C++. And like basically, it kind of takes care of certain things for you. There's a life cycle of a given object. So for like object-oriented languages, you take something where you create an object, you instantiate it, and maybe you kind of all the references to that object disappear. There's a garbage collector that prevents that object from just floating around forever in active memory or main memory. So Golang has a nice garbage collector. Go also has a really nice feature that I haven't explored a whole lot in its like version of threads and threading. They're not as heavyweight as like a C++ thread. C++ thread, I spin that up and it's got its own stack and it's doing all these things and it's pretty heavy. It's heavy in memory usage, it's heavy in CPU usage, whereas Golang's threads are actually a little bit
and well, I mean, it's a language very much designed for distributed systems, so that makes sense. Yeah, it's like that's like its number one of its number one design considerations.
So they do a lot of very cool things in Golang, and actually, yeah, I would recommend going and exploring it. Maybe kind of like, if you were looking at like Python, Golang, and C++, you'd probably see a lot of the different differences and similarities. If you wanted to kind of paradigm shift and test your ability to switch how you think, then maybe looking at like something like Python versus something like OCaml or Clojure or I think F# maybe.
It's like functional
programming.
That's more functional.
Yeah. And I actually, in industry, or at least at the industries that I've worked in, I've generally preferred functional paradigms because it makes it really easy to test. Whereas object-oriented paradigms, it's not that they're difficult to test, but I generally find that people are a little less stringent in their testing practices, and that tends to lead to more brittle practices, and eventually no one can dev your code.
I mean, we've talked about it. I really like Clojure. I want to get like really good at Clojure.
I think I would too. You know,
it's
like,
growing in popularity, and I mean, I think functional programming is. And always has been, I think, since its inception. Yeah. I think languages have more, recently especially started to adopt functional features, even Java, which is kind of crazy to think.
Go figure.
But C# is also great with that, with like link queries.
Right. Yeah, I don't C# too much, but.
But I'm more involved in I teach a game dev course here, and I'm into game development. And recently, I've been considering the idea of making a game completely in a functional, like in Clojure or something, which I think would be fascinating. Because then you're dealing with either the idea of taking your entire frame and performing mutations on it as a state as your state object, or taking just what you would take in like a React app or just a general application, like all your entities, important information, and treating that as your state object. Performing operations on that while still having sort of sequential rendering logic. Yeah. So I don't know. Awesome. I think it would be. Oh, and M. Kloppenberg's Clojure is about the best paying language to know, according to the new SO Insights. Knew about that too.
That's pretty cool.
Doesn't happen to be the main reason that I want to learn Clojure, but it's a nice little.
It's a nice little plus.
It's a nice bonus, right?
You get to hop into a nice, high-paying industry.
But what you're saying is true. I mean, like dealing with state, with object-oriented programming with really large applications, and games are a prime example of this. You don't know what's manipulating what, and especially when you become multi-threaded.
So many side effects everywhere.
Like the nice thing about functional programming is that it scales to multi-threaded systems incredibly easily. Because there's no state. So you're just like a GPU, you spread out all your operations throughout your entire cluster. Yep. And back to the person's point who talked about Golang, and I think that might be an important reason as to why it has a feature in ML, being able to spread out something very easily and very performantly across
take your whole pipeline and put it across the network.
Thousands of machines. That's you could essentially model a neural network with just your machines. At that point, which is kind of insane.
Yeah, so I think it's pretty important. Like, you'll probably want to stay abreast of like some of these kind of heftier languages that are sticking around. I mean, Python's a good example because it's so multi-purpose. But if you're looking to maybe have some more performant systems, and people would be like, oh, you can transpile Python into C, and like there's all things you can do. And that's true, but like, I mean, if you wanted to just out of the box have a slightly more performant system, well, actually a majorly more performant system, it'll always be worth your while to look at C++, but Golang has many of the properties that I think will end up being important in the future, such as distributed systems and well, yeah, actually really just this like distributed systems paradigm where it's like we can spin up many different systems, and that kind of surpasses our hardware limitations.
Yeah, Moore's law is like, at least at the transistor level, is not going to hold.
Not really continuing.
What they're saying is that Moore's law will continue, but it will continue at scale. It's going to be a horizontal scaling issue instead of
rather
a vertical
than
scaling
individual
issue.
cores. Which is really, I don't know, it's a very interesting shift that we're starting to see, and we're all in it. So yeah, also True Kmeans asked, is closure and closure?
They're saying they
do sound the same. Yeah. Sorry, a closure is like you have like function closures. It's more of like related to programming across several languages, whereas closure.
It's a play on the term.
Yeah, it is a play on the term.
It also ClojureScript uses the Google Closure JavaScript optimization library. So there's all these closures.
So there's a million
closures.
Like, yeah, Google one or both, and add programming language at the end, and Google will pop it up. Like, you'll figure it out. Yeah, as Bob Ignite says, functional programming is very easy to verify things, and it's pretty much a exact. Well, I was going to say side effect of the fact that there are no side effects, which is super useful.
And there's been articles written about this too, and how like theoretically this is the reason for software bloat and whatnot.
Yes. And if you've ever worked in industry and you've seen a piece of code that you're like, why does this work the way it does? Where are the unit tests? Why are there no unit tests? Who wrote this? Chances are that they wrote it in OOP and then didn't test it, and they were like, it'll probably work. And so it's like not robust. It does no standard behaviors. All of its undefined behavior is undefined and not documented, and like it's just a huge pain. And I'm actually a huge fan of like languages. Functional languages tend to pride themselves on being self-documenting. So like, and I don't know how true that really is, but it is kind of a nice feature of the language that like, as you write the code, it documents what it does if you kind of follow some standards.
Functional programming.
Yeah, functional programming.
Because it's written sort of declaratively, and that's the word. And it's used a lot in React, and React is actually very functional, especially with Redux.
Right.
It kind of adopts that sort of functional paradigm. But being able to write out explicitly how like the operations that are taken, it's basically the verbs versus nouns argument with programming.
Which is, as a student of CS and you're switching between all these languages, you're like, what?
It gets a little
Why does everyone write things like this? So yeah, we can honestly have an entire stream on just discussing these.
This is turning into a just chatting stream at this point.
Sorry, we will hop back into Kmeans.
For a couple more questions, and then so journal flavor. How old are you guys? I'm 28.
Yeah, I'm 20. we're getting there.
And Nick's already better at coding than I am. So
that's probably not true.
Does Golang have parallel programming? I'm inclined to say almost certainly. Yes, it does.
That is kind of its whole pride and joy. That is kind of its one of its greatest features actually. Is its very solid parallel programming.
All right, cool. Let's get.
And then we're gonna hop into Kmeans. So you'll notice I created a little file here. There are some things in the file. I promise it's not much, and we'll go from there. So I think we did. Yeah, that's the one. And I'm going to use Visual Studio Code. For those of you that have watched streams before, I've kind of amped up my Visual Studio Code a little bit.
I do like how your shell has the Rocky Horror Picture Show sort of ASCII art there.
Every time. I'm going to make this a little bigger. I was actually doing this a little bit last night with my glasses. Well, actually, I couldn't wear my glasses. I had like stuff on my face, and I had to like make this an enormous screen, and I couldn't read it. And I was like, oh, this will be the same size that everyone sees tomorrow. So are you
gonna have anything on the right side of your editor?
Probably not. I'll keep things off the right side of my editor, so that way people can see what's going on. So we have this import numpy as np, very standard paradigm in Python. We also import matplotlib pyplot. I'm a huge fan of pyplot. It's very easy, simple to use.
And these are just tools that are typically associated, not necessarily machine learning specific tools, but tools with numerical computation,
generally,
scientific computation with Python.
Another one you might see is like SciPy. That one's pretty common too. There's a lot of just like these standard libraries that are very easy to use, and you should become familiar with them. The other one is pandas for like data scientists.
Scikit-learn as well.
Yes,
that's a big one.
That's another big ML one. And then if you wanted to hop into like even lower level ML, well maybe not lower level, but other ML, there's like PyTorch is a really common one, and TensorFlow is the other one.
Right, and we'll be using TensorFlow at some point.
Yes, we will actually see at the end of this stream, we'll see something that's built entirely in TensorFlow, and I'll kind of walk through what the code does. I'll point you to the guy who built it. I didn't actually build that one, but that's okay. And then next stream, we'll build a version of that ourselves that is a little bit more customizable. And then this is just kind of an example of like how I can load in an image and display it so that people are a little bit familiar with that. And then we're going to hop into generalizing this, and then we'll walk through my kind of steps for like when I'm working with images.
Shout out to David J. Malin in the chat. If anybody is brand new to the stream, doesn't know, David is the instructor for CS50 here at Harvard University, so shout him out. If you are new, or if you're not new and you've been here before, still say hi.
Yeah. Thank you for stopping by. And I see up there, Journal Flavor says, have you guys been coding since you were kids?
Since I was like 14,
wow.
15.
Okay, yeah. I started here. I started in CS50, so about 2.5 years ago or so. Well, we're getting to like 3. We're getting a little old. But yeah, I messed around with a lot of hardware though as a kid. I really liked putting transistors and
That's
things
got
together.
the spark.
Yeah,
that ignited the spark.
And that was kind of the start. And then I was kind of introduced to cryptography and secrets and puzzles. And then I was like, well, you know what? I'll take CS50, and I loved it. And now it's half my degree.
Kind of like David's story. When he was into computers and stuff, but he wasn't set on CS till he came here, and then now he's the instructor.
And then he ended up teaching that
things
course.
are crazy, you know?
Yeah, it's a wild time. It's always interesting to ask people their stories for pretty much anything that they do. All right, so we grab an image. I'm going to use my own standard naming conventions, but if you have a problem with them, feel free to let us know.
I mean, who wants to write, matplotlib .pyplot,
this
every time?
looks ugly as heck, and I'll try to stick to conventions instead of just my own conventions. But conventions are really not conventional, ironically.
So HWC, that's getting height, width, and something.
Channel, yeah.
Okay, color channel.
So I don't think people actually abbreviate that as C very often. I did because I'm lazy. So generally, don't use single letter variable names unless they're extremely obvious. So I for index is pretty clear.
I was thinking color, but I mean color channel. It's kind of related.
They're related topics, so it kind of works. But if you want to be really clear, you type out channel. And with tab complete, it's really not that bad. But I'm super lazy. And then H and W, you probably should leave those as height and width.
Those are pretty standard.
They're pretty standard.
HW pretty standard.
And you can intuit. We're talking about images. It's okay. So this grabs a single image. So I use the matplot library to pull up that image. It's a PNG, and then I grab its shape and I print that out to us so we can see what they look like, at least as far as shape goes. And then I wanted to demonstrate NumPy's reshaping parameters because that's extremely useful to us. A lot of times when you're working with images, it's not super convenient to use the 28 by 28 by 5 image dimensions. It's much simpler to just use every row is an entire image, and it's just laid out in a way that's meaningful to the machine, but not to us. We don't care. So this reshapes it into exactly that. It's just a single string, a single list or NumPy array of just every piece of data that was in the original image.
All the really dimensions laid out.
Everything's just been laid out.
Single dimensional list.
Yeah, and then this just demonstrates putting that back into the original shape, and then we display the thing that has been picked back up. So I can run this. We'll use Python 3, Kmeans. I run this. You'll notice for this kind of, the image original shape is 298 pixels by 632 by 4. So that last parameter, matplotlib loads its channels in last. If you're using another library, sometimes they load in channels first. It kind of depends on how it's organized, but just keep in mind what your data looks like every time you use it. So the images are originally loaded in like that. I kind of linearized this image, so that's what that second print statement does, is we have this just a single, boom, NumPy array of, what is that, 753,344 just entities. And then when we reshaped it, we get back to the original shape. And then I went and displayed that using matplotlib. And you can see that that is our first image. There's some axes here, and you can remove those if you'd like, but we don't particularly care. Now, if I wanted to kind of remap this a little bit so that everything was a little bit easier, maybe for computers to deal with, I could do something like this. Whoops, our color mapping doesn't work here because our image pixels are not translated into a 1-odd scale, but we can do that shortly. So essentially, what's going on here? I saw someone asked in the chat, what does channel mean in context of an image? And that's a great question. So if we have images that are in black and white or grayscale, those are single channel images. So every pixel, the intensity of gray is represented as some number from 0 to 1 usually, or 0 to 255. And that allows us to just scale across one thing. But if I had an equivalent RGB image or color image, it's a third the size. Because you can think of an image as really being a composite of, and there are different ways of organizing this. This is just a very classically taught one, where I have actually 3 versions of the image kind of overlaid. And the first version version is the red version, the second one is the amount of green, and then the third one is the amount of blue. And then when I combine those on a computer screen, I can then see what the actual colors originally were, actual colors being an approximation. There are other ways of doing it, using like hue, and I think that one's 4-channel, so this is what we're using. But it doesn't really matter in our case. We can kind of shuffle everything over and then readjust accordingly, kind of as needed. So hopefully that clarifies what reshaping things does here. I am just going to try and stick to these 2 libraries. I might also throw in the TQDM import TQDM, which I don't actually know what that stands for, but it's a really like pretty way of printing out as you iterate over something what it looks like, and it's just kind of a good way of keeping track of stuff. So we know we're working with images. We now have a way to reshape, remake, readjust images depending on what we need to do, but we don't necessarily have a script that does anything meaningful. So I'm going to start my script using kind of the if name main paradigm. Oh, thank you. Someone in the chat says TQDM means progress in Arabic. I don't want to butcher that word, but I would otherwise try and pronounce it. That's really cool. Didn't know that. So it displays pretty progress bars. It's really useful. It just helps me kind of mentally keep track of where we are in the execution of code. And then you'll see that the paradigm that we're using is kind of like, if this is intended to be a script, let's use it as a script. So what we're going to do is, if name is main, then what I want to do is I want to say my data is some method where I call like load data. And then I'll probably have to give this some directory. So if I go into my terminal and I list out which directories I have, let's have it load data from the stream all directory. So it assumes relative pathing. And that loads in my data. I want to pre-process my data. So we might be very clear about this and say pre-process of data. And from there, I now have all of my pre-processed data. So what I might want to say is, OK, we have our pre-processed data. Let's build a Kmeans classifier. So we'll call that Kmeans. And that's going to be equivalent to some Kmeans classifier, which is instantiated with some number of classes. So we'll say k equals, I don't know, we'll have it be a binary classifier to start, but we'll change that shortly. Already we're starting to see there's some magic numbers, there's some functions that we really need, all sorts of interesting things that you need to know. So from there, we have this Kmeans classifier. We're going to use kind of the standard like sklearn methods, and we'll say have it fit on the processed data. So once it has been fit to that processed data, we should have some set of images. So we're going to do, this one deviates a little bit from the standard API, but we're going to say Kmeans display means. So this will display the mean images to us. And then, yeah, actually, we'll stop there.
So let's work through this one line at a time again.
Yeah.
So load data stream all. So what is it loading? The images from the stream all directory?
Yeah. So I handed a directory, and it assumes that there's some set of images in that directory and snags all of them for us as numpy arrays. So this kind of way of coding things is something that I really like doing. It kind of lets me template out my code. I kind of know how things will work, and it gives me kind of a set of objectives to then complete. So I say, OK. Load data, and basically it self-documents or writes it for me. So this should take in some like directory, and it should return to us some numpy array containing
sort of Haskell-y sort of syntax.
Yeah, so I am writing a little bit in kind of functional style language over here in our comments. To clarify these comments, make them a little bit easier to read, we'll do that.
Oh, nice. That's
yeah,
cool.
I've customized the SC.
That's an extension?
Yeah, there's a bunch of extensions.
Someone was asking about
here.
the code time extension on the bottom.
Oh, yeah,
right?
that is also an extension. I'm a huge fan of using extensions to kind of, I don't know, make it feel a little bit more homey. And someone asked which IDE is that. That is an incendiary question for some people, but this is Visual Studio Code. I'll leave it to you guys to hash out how much of an IDE it is. Mine functions very much like an IDE. I would count it for all intents and purposes as an IDE.
It's definitely more so than a lot of the like competitors like Atom and Sublime, which aren't IDEs per se, much more text editors. There are some IDE features that VS Code gives you.
Yeah, especially I'm a huge fan of the way the terminal integrates, where whereas in Atom, you have to like drag the terminal, and I haven't quite figured that one out yet.
You have to install it as an extension too in Atom.
It's huge,
in this, it's native in VS Code, which is really
so
cool.
I'm a huge fan of Visual Studio Code. Very well built. I have not had any problems. Pretty easy to use. And so then we have this pre-processing step. And so anytime you're working with images or audio files or really any kind of data, but we're going to say just kind of those two in particular because they're easy to contextualize, we might want to like manipulate that data somehow. So in the case of images, a lot of times that means extending our data set because it is kind of difficult to obtain images that are meaningful. But as we mentioned a little bit before, and we're going to mention probably a couple more times, an image of like Colton and I here, and we're actually probably not going to do this in this stream, but it would just take a little bit more time. An image of Colton and I sitting here as opposed to an image of us in reverse, we're still in the same stream, right? So there are ways for me to extend the amount of data that I got out of something, even though I never like acquired new data. And so that's kind of an image augmentation process. Audio files, it's a little bit more difficult for us to kind of imagine what is a meaningful like audio file augmentation versus not. But images is pretty easy for us to understand that like if I swap us around, if I make us black and white versus color, they're all still the same. So, and there are different arguments as to which ones are more the same than others. And so pre-processing is usually a pretty important step on your data. Now, there is a huge need and kind of problem in the data science world at the moment where we have many different versions of data sets, and it can be really difficult for us to keep track of each of those versions, know who created it, how it was created, what it means. And so there's actually a white paper out there, I believe it's called Mystique, that talks about the different versioning systems. Oh, sorry, no, it's the something DB, bolt-on versioning system for pipelines or data pipelines. If you Google around enough, you'll find it. But there are very many cool papers out there on all sorts of ways to like handle the new data that you create given an original data.
Is this pre-process like an optimization for our machine learning?
Yeah,
algorithms?
So we'll actually, the step that we'll take is to center our data and normalize it. So standard normal is something that is it's a distribution. It's kind of what people mean when they say normal distribution. They actually mean standard normal, which is something that is a Gaussian distribution about the center of mean
That's a bell
0.
curve, right?
Yeah, it's our bell curve. Looks like this. It's centered on 0. So on well, not on average, but kind of like at the halfway point, you're at 0. And it has a standard deviation and variance of 1. And that's the standard normal distribution. So in order to get any set of data into a standard normal, you can subtract the mean and then divide by the standard deviation, and that puts you at a standard normal. So we will do that in our pre-process step. We're also going to reshape our data. So given a data set that is like an n by image parameters set of data, we're going to actually take each of those and then hop them into an actual, like the single line versions of those images, which will make it a little bit easier for us to do some of the math on them.
Right, just turning into a matrix, basically, right?
Yeah, exactly.
A flat matrix.
We want like an n by however long our images are matrix instead of like a n by 298 by 695 by 4 in like this 5-dimensional matrix. It was a huge pain. So we're not going to do that. We will pre-process a little bit. And kind of keeping with our documentation, we want this to take in some numpy, we'll say n by like height by width by channel data, and convert that, well, we'll be more specific, numpy array, and we'll convert that into an n by height times width times channel numpy array, possibly normalized. So what this should do is normalize our data possibly. We'll actually run this first without the normalization, and then we'll add it in. But it, at the very minimum, should perform this transformation. And that is kind of how I write my documentation.
It's just easier for computers to perform these matrix by matrix operations too, right? So
it's very easy to do just full
matrices.
matrices.
Use a single matrix.
Yeah, exactly. So then our Kmeans classifier is going to is literally just like the classifier object itself. So this is where we're moving away from our functional paradigm. And we'll just do that.
Yeah, creating an object, a Kmeans classifier object. What is this from again, the Kmeans classifier object?
We'll be building it.
Oh, so we're doing this?
Yeah,
okay.
Yeah, we're doing a full full thing.
Respect.
Yeah, so this doesn't exist yet. There's no library to pull it from.
Does preprocess not exist then either? Because
none of these exist.
Okay, got it.
So we have basically designed what we want everything to flow like.
Got it.
Sort of like a
top-down approach to software engineering.
It's my top-down approach to building this.
I like this for game development too.
It works really well. It gives you kind of direction. You have some goals. You know what things need to work. And in concept, this is complete. Like the actual script part of it works fine.
Yeah.
So that's useful.
This is kind of like what you see in test-driven development a lot too. You'll see people build their actual application and like test these individual functions as they're writing them after they've already been created, which is kind of cool.
It's actually a very cool paradigm. I'm a huge fan. I think it just makes my life easier. I'm going to say of data, and this goes to, so once we fit, this doesn't return anything, so I'll say it goes to none. We just want to fit the data, and again, this is where we deviate entirely.
Usually when you see return none, it's
that's
very
just, we're not functional. This is pure side effects.
Pure side effects.
So now our Kmeans classifier has some state, which is what we kind of mean by our comedy over here, is like, it just doesn't. Any print statement is kind of like that too, and this is effectively a print statement. So essentially what we say is .display means is actually going to it doesn't take in anything and it does nothing.
There is some degree for a lot of applications where you still need some bit of like state, some bit of input from the outside world and
pure
output to the outside
kind of
world.
a pain.
I mean, even enclosure for input and output, you do need to use.
You still print.
You do need interfaces to humans,
which is kind of where we end up deviating a little bit from functional. Even OCaml, you have like print statements and stuff. Like you just there's some parts of it you have to.
Yeah.
And I guess the argument that you don't have to is like you could write it to file or something. I don't know. There are like a couple of people who are like, no, it has to be pure, and I'm like, yeah, I don't know. So we're using like a mostly kind of functional inspired. We'll call it that.
It's feeling pretty imperative to me at the moment, but
it's pretty imperative. We deviated far from functional pretty much after this point.
Functional core with OOP edges are imperative.
Yeah, we'll say it's pretty much all imperative. There's like a functional bit at the beginning. We now have kind of set up all of our stuff, so now let's go start building some of these functions. I'm going to leave this template code up here for a little bit, but it'll go away eventually. It'll actually go away very shortly. So we have to define a function, load data. That has to take in a data directory, and it's going to return to us some numpy array. And so this is kind of my template code for that. I'm going to remind myself of how it works by copying over my documentation comment. And what we're going to do is, for loading in our data, we're assuming something about the data directory, which is that it has a bunch of files that are PNGs in it. And in order to access that in a really convenient way, we're going to just import OS. So lets me interface with the operating system pretty conveniently. I'm going to comment out all of these lines so that I can run this code, in order to test it.
One step at a time.
Yeah, one piece at a time. So I just want to verify that
you could just write all the functions as stubs and just
and then get it to like mostly work. And I think that actually is generally a little bit better practice, but we're gonna kind of go from there. And so once I want to load my data, I actually am going to just print out what os.list_dir of data directory looks like. So I know that I'm going to list out the data somehow, and I know that in some variant of this, I'm going to need os.list_dir. And this is my running of kmeans.py. Oh, sorry, I'll stop displaying that image. Forgot about that.
It's a good quality image.
Yeah, it's a very nice image. There's us two in there. So here are all of the things in that first data directory. You'll notice that there are approximately, maybe you wouldn't notice this, but I happen to know it's about 40 images in there.
As the one who cut the images.
Yeah, I was going to say, there's no way you would notice that. That's literally impossible. But unless, maybe if you're like a savant. There are about 40 images in there. There are exactly 40 minutes in there. 40 images in there. And that's all I really need to know. Now what I could do is kind of like a list comprehension on that and say, oh, actually, I want like os.path.absolute path, of f for f in that list directory. And now when I rerun this, it now tells me, whoa, what's going on there? It now tells me the absolute path of each of those things. So if you want to be a little bit more paranoid about like which actual file are you using, you could do this.
Love list comprehensions. It's people have
very succinct.
People have described them as being very functional in their design.
Yeah,
they're essentially map
clean.
filter
Yeah.
They don't have the like a reduce capability in them as far as I'm aware. I mean, you could write a function. You could write a function and then apply that.
Right. And there is the lambda calculus. Like you can create lambda functions in.
Yeah, you can. Yeah. I hate how limited lambdas are in Python.
They're much less complete.
Yeah, it sucks.
It's really just like a kind of someone said lambda is.
It's basically like a JS like an ES6 like return statement. It's effectively all lambdas are, which is
exactly.
Which sucks, but it could just be my own ignorance. But I'm not a fan of Python's language.
I'm sure you could eventually kind of like you could build your own kind of library around it. And I'm sure people have, but we'll kind of just generally all agree that it kind of messed up. Oh, I see Ellen1 says, are all CS majors at Harvard this well-rounded? Brian is linguistic, also does web. Harvard does a pretty good job of like forcing you to do a bunch of different things.
Does it look for like extracurriculars? It does a lot for when people's applications, right?
Oh yeah. So when you're applying,
I'm not a Harvard student,
like, you're all over the place. Yeah. I actually was like mainly a musician and martial artist in high school, and then I kind of switched here and flipped over to all sorts of new things. And I think that I can't speak for the entire student body, obviously, but I think from the people that I know, and there's enough of them that it's like people are pretty diverse. They have pretty diverse interests. Like I actually have a fairly major interest in like government and economic policy, which is very unrelated, and I have a major interest in music theory, but all of those things do not show up in my actual major. I'm also a pretty major student in like Chinese, although that deals a little bit with my heritage. And so for my personal story, we're all over the place. And a lot of students I know, like Brian's linguistics and CS, and he does all sorts of like things with the intersection of those two. But he's also, I think, pretty musically inclined, very nice guy, does all sorts of things with like the newspaper and stuff like that. So all sorts of interesting things out there. And there are many people who are just kind of like, oh, you know, I'm like a world-class ice skater and I also study pure math. And like there's just very diverse intellectual pursuits.
Do you know how to read this?
Yeah, so that asks roughly if I speak Chinese.
Because I recognize that as being Chinese, those two characters at the end. Because there's some overlap between Japanese and Chinese.
Oh, right. Oh.
Which I know a little bit of Japanese. This one means to meet, I believe.
So it can mean that in Chinese as well. But in this case, it's like have the ability to, or actually,
like ability to Chinese is basically what this is asking.
That's roughly what that reads in English. A lot of times, if you were speaking it in English and then translating to Chinese, you would add another verb between kind of those two middle characters, and that would allow you to indicate from like an English speaker's perspective, like, do you have the ability to speak Chinese or the ability to understand and so on.
Compared to Japanese and Chinese, English is very bloated with all of our particles
so many words.
and all sorts of other components of our language. They're very sort of implicit.
They're just kind of like, boom, it's there.
Speak the things, and then it's like you understand through implicit meaning, which is kind of cool.
It's very interesting. Although they also, at least in Chinese, there's a lot of these like kind of particles at the ends of sentences, and I never get them right. Like it's just I'm always a mess. And they're all just like single syllabic, kind of like la, n, ba, and so on. And it's very, very difficult for me as a native English speaker to be like, well, should I put that there? Should I not? There's also a lot of those particles that start sentences, and they're like meant to imitate sounds.
I mean, a lot of it is probably like pretty, like you learn it through exposure. Right? You constantly hear it, and you constantly get those contexts.
Right,
like
exactly.
in English, like the word even, like do you even do something? Like that's probably not.
That's exactly.
Like there's a lot of words like that in English that we just put into sentences that are very native sounding, that make a lot of sense, but to people learning English as a second language, it's not clear.
It's just like, what are we, why? So I'm positive that when I speak Chinese, I sound very much like an American. I have a bit of an accent as well. But when I was in China, people were still able to figure out what I was saying, and it was very nice to be able to make friends with people who didn't speak English. That was pretty cool. None of my coworkers spoke any English. At least they spoke some. I think my PI actually spoke the most, but everyone else was pretty non-English, and it was fine. They're all great people. I learned a lot about their lives. It was very fun. So if you ever get the chance to learn another language, go for it. It's very cool.
I think the moral of the story is that it's nice to be curious about things.
Yes.
And I think that's, if you have general intellectual curiosity will naturally lead you down many branching paths. And I think a lot of the people here have that, and not just exclusive to Harvard, obviously, but just in general, people that are interested about the way the world works and the way things work and are, want to explore that. Yeah. You'll just develop interests and hobbies all over the place.
Yeah, exactly. You hop all over all sorts of different things, and if you really like something, you'll get good at it, roughly.
You can try.
So you can try. So, go go and be you.
And don't bully English as Al Robot Wizard. Would never do such a thing.
We would never do that.
But English is an interesting language.
But yeah, it's a very interesting language. All right, so we're gonna plot.imread of f for f in image files. The reasoning for me splitting these two is not major. I just wanted to make it a little bit easier for people to read. As you can pretty clearly intuit, I could throw plot.imread.
You could make it a nested
here.
comprehension, or or
even just
in this case, you wouldn't need to make it
yeah.
a nested comprehension. You just
it's
need
not terrible, but I just wanted to make this a little bit. I don't know. I guess pedagogically it makes a little bit more sense for me.
It's already pretty bulky as it is. So
yeah, there's kind of a lot of information in there. I think this is fairly reasonable for people to read.
Yeah.
Sorry. So now, roughly, we think that this function returns what we think it does given its input. We're going to just double check that. That's rough.
Users, Nick.
Oh, that's rough. Yeah,
That's
there's
weird.
all sorts of errors here, which is awesome.
It's saying couldn't find the path, which doesn't make sense.
Yeah, especially given that it's an absolute path. Let's debug. We'll do some debugging. Live debugging is kind of our favorite thing to do here.
Yeah, no such file.
Is that really true? Oh, right. Yeah. So absolute path is a little bit of a liar. We're gonna do something a little bit funnier here, and you guys may recognize what I'm doing. So this will, I think, work. Yeah. And basically what was going on was it was emitting the actual data directory. So absolute path is a little bit silly, I guess, in how it works.
I see. Okay.
It works given the absolute path to where it was called, and then it just appends files on there as is. So you could do like an os.path dot absolute path of this.
Starting to get real nutty.
That looks a little wild. So for readability's sake, I'm going to remove that. We will. Oh, sorry. Also, we will put this on a GitHub.
That'll be good. That'll be good. Yeah.
So you guys will be able to access this later. But I'm actually going to remove that just for readability's sake. Yeah. So hopefully this all makes sense.
I hate how bulky os.path calls get in Python. It just like they span like
They're
7
enormous.
lines.
It's a huge pain. So we're going to try and avoid having too many like enormous line functions. But here you go. All right, so our data loads correctly. We end up with a NumPy array that is this n by h by w by c, and we can verify that here because I printed out that shape. We have 40 images, so that's n. We have our w, which isn't actually the w, it's actually our height, but we don't really care. Oh, I actually did call it h here, so my head beforehand was correct. The way that I'm speaking right now is off. So that is the height of the image, and then the width is 632 pixels. And then we have 4 channels, so 4 things below. I always forget the other names of them. I know hue is one of them. I don't know the other ones.
Hue, saturation.
Contrast, I think. Maybe.
I think contrast.
That might not be one.
Sure.
I'm not a huge expert in that.
I think that's a macro. That's a macro, an image macro feature, not a
right.
per pixel.
It's not a per pixel thing. That's a great point. So yeah, if you just go Google like a way to convert from like hue to RGB, it'll fill in the rest of them for you. Yeah. So you can go Google that. So now we need a way to pre-process our data. So we're assuming that we have some data. I'm going to copy my comment over. And we're not going to normalize it first, but we will eventually. And I now want to define some preprocess function.
Hue, saturation, luminance.
Oh, thank you.
There we go.
That's hue, saturation, and luminance. That's that.
Oh,
well,
filmmaker colorist.
That
That's cool.
For those of you who are just kind of listening casually, I guess I do that with YouTube sometimes. Pac-Man said that hue, saturation, and luminance are the 3 things for converting from like the hue version to the color version. And they end up in the same image. And then they said that they're a filmmaker and colorist, and we were like, yeah, that makes 100% sense.
There's some really cool stuff like when you use the HSL or HSVL model for color modeling in games. Like you can actually I used to be really into procedural generation. Actually, you know this from the class.
Yeah.
But you could take if you wanted to dynamically texture, like let's say you have a sword and you want to dynamically recolor the sword. Doing that with RGB looks horrendous if you're just using random algorithms because you get these crazy nasty colors. Yeah. But using hue, you can just modify the hue a little bit while keeping the saturation and whatnot, and it actually looks much more coherent.
That's a very good point. Yeah.
So these different color models work well in different contexts.
That is a great point. Yeah. That is a very good point. Yeah. And then the True Kmeans points out that our 4th channel in our version is opacity. And so you'll notice that our data is actually not RGB data. It's this hue, saturation, luminance, and opacity data, which is way less catchy. Sorry. So HLSO. Slow.
HLSO.
Yeah, I'm not going to attempt to say that anymore on this on this stream. Yeah, it's a little weird. So I'm going to just leave that one as is. You all can read the chat if you want. So we want to pre-process the data, and we're basically just flattening the data. Is the first step that we're going to do? So what we want to do is just kind of, I guess, flattened equals np.reshape.
And this is what we did earlier. Now we're just putting it in a function.
And so if you remember,
all of our data.
it's up here. We're essentially just doing this.
Right.
Now I do have an extra parameter in that I have like the dimensionality of the data. And so we're going to say nhwc is equivalent to data.shape. And we assume that we're given a numpy array. Sorry, no error handling, no malicious input or malevolent input to testing.
It would take ages to finish if we did this like the actual.
This isn't industry code.
Sorry,
it's just not going to be the way that everyone wants it to be. And then we do h times w times c, and this is now hopefully. And we're going to just kind of, as we build each of these, we're going to just double check that we get the things that we think we get. And this is going to be our new data. So at the moment, I'm going to just re-alias this. So new data equals flattened. And this allows us to put like another pre-processing step in the middle, which I happen to know we will be doing later. Otherwise, it's just slightly less convenient. So we go ahead and do that. And essentially what we get is this here at the end, which makes perfect sense to us. There are 40 images, and then there's just the things at the end, each pixel. So once we've done that, we now have our flattened data, and this makes perfect sense, hopefully, to everyone watching. This is our pre-processing step, so our data has now been pre-processed.
We just basically turned into a bunch of numbers. We converted our image into a flat line of numbers, and now we just have like 40 lines of numbers that we can perform math onto to do magical things.
Exactly. And so we're going to delete these pre-lines that we had up here. So now that we've pre-processed our data, we look down and we recognize that the actual Kmeans classifier is what we have to implement next. And so that's an actual class. Kmeans classifier, gotta love autocomplete.
Get a little bit of object-oriented programming in today's stream. Gotta love it.
And we're going to define an init method. So for those of you who aren't familiar, an init method is the thing that gets called when a object or a class is initially instantiated. And so what we can do is we can set its default class to 10 as if we were classifying MNIST data, which is pretty convenient. As is pointed out by Circef, pathlib is very convenient on handling paths. Yeah, that's a great point. I use OS because it's built in. Pathlib might also be built in. I'm just not familiar with it. But I will probably look at it right after. Stormy Dragon says that according to PEP 572, wow, you guys are wild. Assignment expressions can be used in lambdas will be in Python 3.8.
Yeah, have you seen that? You know, like in Python now, you can't assign a variable. You know how like in C, it's very common, or Java, to assign like in an if statement, you'll be like, if k equals blah, 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 some condition.
And you assign
and then
check
k gets the value, and then you can use it. You can't do that in Python now.
Right.
But they're going to add that in 3.8, and you can use it in a lambda expression.
It's almost like we're being inspired by C++.
A little bit.
Go figure. And I'm sure the Python developers are like, oh my god, that's fault. Like, what are you talking about? Yeah.
Well, Guido left, and I'm pretty sure a lot of these hangups were reasons that he wanted to leave. So based on what I've heard, it could be incorrect.
Yeah, Guido, if you're on the stream, let us know. Tell us what you think. All right, so we have this init.
He's like, Guido Manrosen, this is a terrible idea.
Like, this is horrible.
Like, you guys suck. Why are you
Why are you doing this? And so we're going to define this. We're also going to just define a mean images parameter, which is going to be a list eventually, but it's going to be none at the moment. I kind of, in my init statements, I like to just include all the like things that I want to be global. There are naming conventions for these. I will admit I'm not the best at following them. Like things that are internal should really be prefaced with this or end with an underscore and so on. But I'm gonna just pretend everything's public in our objects, and it's fine-ish, question mark.
Yeah, Python has very loose object orientation sort of principles compared to language like Java.
Exactly.
Everything is very protected. In C++, it's actually even more stringent, I believe.
Really?
With its classes.
Oh,
you have to specifically allocate friends
public.
For. It's been a long time since I've done C++ OOP. I just remember it being tougher to do what you want to do compared to Java, which is like miles tougher than Python, where you can just do whatever you want.
Yeah, exactly. You can just do.
I mean, it's dynamic languages versus static languages.
That's a good point.
Oh, Sergey says he strongly supported this idea. Oh, that's cool. Okay, I'm glad to know because I think it's on. I actually think it's a cool idea. We actually ran into it being an issue with the C++ or with the CS50 code base. That assignment expression thing, and we needed to find a way to work around it. And so the fact that they very timingly are adding it to the language is kind of cool.
Yeah.
All right, oh, sorry. So explain what you just added here.
Oh, yeah. So I was adding some template codes, some things. I can now run this entire file, and nothing will break. I think.
Okay, gotcha.
Nothing will also
an empty
break.
class right now for the most part.
It does nothing, but it kind
it.
of works. You know, like our data, all of our methods kind of function-ish. Like they won't fail. As Bhavik Knights points out, everything is public in Python. There is no private. They just pretend to force it using the __ paradigm. And you can kind of see that if you run dir on something. Like if you just we could print out dir of something. Print dir of Kmeans. And what this will eventually tell us is there's a bunch of attributes. You'll notice a lot of them start with this double underscore.
They're called dunder, usually dunder methods or dunder fields.
Exactly. Or for those coming from like that Java C++ paradigm, those are your kind of private methods, but they're not like strictly enforced private. Like I can still access them, they're still available. It's part of the API. It's just not intended to be.
A lot of these are meant to give objects default default length abilities, default.
Stir. So if you wanted to print an object, you always have a method to do that.
Part of like a unified API for Python objects, which is like why dictionary sets, lists, and all sorts of other things can use the same set of functions.
Exactly. And actually, just to kind of highlight that, we'll redefine the stir function for our Kmeans classifier. And all this has to do is return a string. That's the sole requirement. So we'll just say this is a Kmeans classifier object, k equals, and we'll just format that with self.
Oh, you still use the dot format?
I do.
You don't use format strings? Oh, come on.
Here, we'll switch over. As Colton has pointed out, I'm getting old.
That's an old school. That's old school, man. There you go.
And
how
so
much
now we have this beautiful format string.
Come on.
No, that is a very good point. I should switch over to format strings. So what this does is essentially the same as what I had originally typed, but it's a lot more readable. I agree. Where you just kind of if you work in like jQuery or JavaScript, you can do the same thing
template literals,
with template literals. And so I just add an F to the beginning of my string, and that lets me use these curly braces to indicate something where I just write out Python code.
To your credit, I used the %. I used it overall. No, I don't use it now, but I used it a lot. Like even as 3.6 was still out, I was still using % because I was actually still in like 2.7 mode.
Right.
So I didn't really get too used to the dot format. And then
you see that all the time.
When format strings came out, I was like, this is nirvana. I was like,
they're so nice.
This is how you write strings in Python.
It's so much nicer, and I can't wait for that to be the like standard in all the tutorials everywhere. But yeah, there's all sorts of like funny things with this. So instead of now printing out a dir of Kmeans, we're actually going to just print Kmeans, and you'll notice that essentially when I run this, it'll print out the object that I told it to print. So essentially what's going on here is it just took this and printed it instead of whatever it would have printed by default.
Which would have been like some Kmeans classifier object at whatever.
Yeah, this is what it would have been, which is kind of a literal version.
Yeah,
it's the
gives
default
you the address of the object.
Yeah.
And then Stormy Dragon actually mentioned that methods with dunders on both sides, like stir, are not hidden like methods with prefix dunder. Prefixing will obscure the name by adding the class name as a suffix. That's actually kind of cool.
That is a good point.
Like a sort of sloppy privatization method. Yeah. It works, I'm sure.
It does.
But it's still not.
But it's not as clean as a C++ enforced class or a Java.
Oh, and actually, Bhavik was mentioning the preservation of dict order with 3.6. That was such a nice thing.
Right. Thank God.
Because dictionaries, obviously, they're hashed, so they don't have a predefined order or an order set in stone.
Yeah,
C Python by default as a 3.6 makes that a thing, so you don't need the ordered dict class anymore. That would be a thing that you used to need to, instantiate.
I don't know if I've ever used the ordered dict class. I feel like I always just worked around it. I was always just like, I don't want to figure this out. Yeah.
I mean, generally when you're using a dictionary, you're like not always concerned about the ordering, but sometimes it's important.
It can matter, and a lot of times it's not worth reinventing. As is going on in the chat, people are clarifying that dunder methods refer to these with double underscores on either side. We were kind of just skating over the fact that private methods have only a single underscore set. I was kind of implying that, but using an example that actually has both. So keep that in mind. We won't mess around with private and public methods at all here, but it's important for you to know. Yeah, so we now have defined our kind of init roughly. We have this stir. And now we just have to define how fit is going to work. Now, fit is kind of an interesting one because we have to define like the number of iterations that this has to go through to fit. We also have to initialize our fit. So it may be worth our while to have another method that is like init kmeans. Or something like that, basically to avoid it conflicting in our heads with the init method. I'm not quite going to put that here, but it is kind of the right idea. We're actually going to just put it within the fit method, just for convenience. So we do need to initialize, given our set of data, what each of our clusters is. So what that might mean for us is we have to say, OK, our clusters are going to be some set of kind of lists, and each list has all of its individual things. You'll notice that we're going to actually kind of take a hit to performance in terms of what we're doing here. There are ways to do this that are much more performant, even in Python. We're going to avoid those for clarity, just as a disclaimer. So the clusters is going to be some list of each of our clusters. Now, I could initialize that list, and actually we're going to, I guess. It actually doesn't really matter. And because of the way that we're going to do this later, we're not going to initialize those yet. But we are going to shuffle our data. So np.random.shuffle lets us shuffle our data sequence. So it's going to shuffle our data such that things that were originally in one order are no longer in that original order.
This is good because the images currently are like grouped by stream, basically.
Right, exactly.
I'm assuming that's why you're doing that.
Which is why we're going to do it this way. So we're going to shuffle our data, make sure that everything's shuffled. Here's some of the documentation if you'd like. Oh, actually, this is a documentation for the random one. And we're going to, let's see if there's any important things. This doesn't return anything, by the way, so that's why I don't actually have to like have it capture anything.
More
so
side effects.
Very non-functional. And it is kind of annoying to me in Python. Like, there's no real standard on like do things return stuff or not. Or maybe there is, and they've like migrated towards that standard. But for a while, you could like there were some things that you shuffled, some things that you didn't, things like that.
Yeah, there are not streams. There are functions, like native functions that differ, like within the standard library.
Yeah.
Like
I think like reverse and sort are an example of those.
One does an in place and one does a return. So it's weird. Yeah.
It's just like why weren't we just consistent?
Started asked why is tomorrow's stream earlier than usual. We're trying to gravitate a lot of our streams earlier. Due to Nick's schedule, his tend to have to be a little bit later in the day, but mine are going to be probably around noon most of the time. So keep an eye out. Is this the news shuffle by default?
Who did say it? Not sure. It's probably
something similar to that.
Yeah, you can go Google the documentation, see which shuffle
they might have a fancier algorithm. Who knows?
Also possible. I don't think it's np-random.split. It's maybe it is just split. Yeah. Oh, okay, cool. And I don't really remember the syntax for split, so we're gonna use my fancy IDE, and it's going to say split our array into n sections. Cool. So what we're going to split is our now shuffled data into k parts. So self.k parts. For this and for using split, you'll want to make sure that like your number of data items is divisible by k. Otherwise, I believe split throws an error. So if I throw in like a random prime number, actually we only have 40 data items. And there's not that many things it's divisible by. So if I threw in something like 9, it would freak out.
No potential way to get around it.
Yeah, no solution. You just freak out and cry. No, there are ways to solve that, but we're gonna kind of use this because it's convenient.
So we're just doing a randomization of our first clusters.
Yeah.
That's just purely random.
Comment this. This is a random init for the first clusters. And this just sets us up so that we have a bunch of random images. Now, it might be really entertaining for us to like print out these random images before they've actually been fit, so we could kind of show that. But now we just iterate over. So basically what we do is each step we say, OK, here are our clusters. For each item in our data, see which cluster it is closest to and assign that to a new cluster. And the way that you kind of check which cluster it's closest to is you look at the mean of that cluster and you say, OK, well, you know, what mean are you? What is our distance by some method? And then we go from there. and we assign it to that cluster.
It'd be a little bit of a bulky line of code here.
Yeah, we're going to kind of break it apart into a little bit of some new pieces. So we also need to calculate the cluster means.
Are we going to do a recalculation of the mean as we resort the data, or are we going to pre-calculate the mean, do all the fitting, and then rinse and repeat that several times?
We're going to do the second part, where we're going to calculate a mean, and then we're going to iterate through all the data and be like, all right, what things do you have in, how close are you?
Remap to the clusters.
Reassign, recalculate a mean, and then do that again.
And then how many iterations of that do we typically do?
So actually, we don't do that many. A lot of machine learning algorithms, you iterate constantly, and you're kind of iterating forever, and it takes a while. And now, if you have a lot of data, this can still take a while. But we're actually only going to iterate maybe. We'll display the results of different iteration numbers and kind of look at what they look like, but we'll probably only iterate around 10 times. And we can kind of measure that difference by measuring the loss across, or some random, not random, but a choice of things as far as what breaks down or what is costing us. So we have our clusters. Now we want to get those cluster means, and we know that mean images are those cluster means. And we want to assign that to the mean of everything. We want to assign the means of each cluster to these mean images.
So we do cluster.mean for cluster in clusters?
Yep, very close.
np.mean of
cluster axis equals 0 for cluster in clusters.
Now what's the axis equals 0?
Right. So the 0th axis is the first dimension, and the first dimension is each image is one of those pieces of that first dimension. And so I'm just saying I want the mean across images, not the overall global mean. As if I just sampled across the whole thing and took a mean. I actually just want the mean per image. So what this ends up resulting in is if I have a group of images, then it actually creates a mean, what that mean image might look like, which is very useful to us. And so actually what we're going to do is display the images right after this step. So essentially what happens is now we have in self.mean images, we have a mean for each of our clusters, for each of the K clusters. So what we're going to do is self.display means, and then we'll stop execution there. We haven't finished fitting or done any fitting whatsoever, but we'll do plot.figure, and then we'll do for K, we'll say K and image in self.mean images plot.imshow of image. We'll reshape it so it looks a little bit better. Reshaped with a D to make our variables a little bit cleaner is np.reshape of the image itself. And you'll notice we actually don't have the dimensions established here, which would be very convenient for us. So we're going to kind of establish the height, width. Oh my god, I can't type, I swear.
That's the stream
and
curse
channel. Though. It really is. Every time. Height, width, channel. Just telling Python that we want to use the global versions of those, and you're like, what global versions? Great point. We'll go create them in a sec. And then we'll just plot.imshow and plot.show. We'll give it a title so that we know which one we're on. Mean.
So this can show a slideshow, but a list of images that you click an arrow to go back and forth. I'm not too familiar with matplotlib.
That's exactly it, actually. Nice. I'll use Control-C and just exit out of the images.
I'm so happy that you're using format strings now.
Yeah, I'll switch everything over to format strings just for everyone's convenience. And that will be kind of the way that we display all of our mean images. So for those of you who aren't familiar, this should be enumerate. I was like, that doesn't work. So enumerate, it just takes an iterable, and then it gives me an index as the first thing out of that iterable. It's really convenient.
You would get an index by default when you just use for.
No, you would just get the image itself. And it's really convenient for my title to have that iterable. There's no real reason otherwise. For those of you who scream lack of performance, yeah, well, that's true. And basically what we do is we have our self.mean images, which is a list of each of those images. And what we're going to do from there is we're going to grab the image and its index, which is whichever cluster it represents. I guess it's for human readability, we'll do +1. And then we have our reshaped version of the image, which is what we did kind of way earlier, where what we said was we're going to reshape the image, which is just kind of a random, like, or not random, just giant list. It's not random, I
We
promise.
could try with random, but I don't know if that would work.
I'm not going to show you a whole lot, but it looks pretty. It's just a list of the image's pixels and items, kind of I got to stop saying random, stuck out there. And we're just going to reshape that into what a conventional image might look like, and then stick that into imshow.
This is putting it, basically that single dimension thing back into an actual like image package.
Exactly.
Like the format that we need to render an image. And someone, Eric was asking a question from our Python, why Kmeans instead of dbScan?
Right. So I think that Kmeans is just very easy to explain. And also it helps us motivate our requirement or our desire to generate images. So in my head, when our actual original intent was to build a generative classifier to show you guys, and I was like, well, that might be a little bit too big of a step to start, so why don't we start with Kmeans, which is really easy to kind of intuit and explain, and then from there we'll motivate our generative classifier by saying, well, Kmeans can't really generate new images. It's not built for that. So then we might go, well, but what could? And then we'll say generative classifiers, and that leads into the next stream pretty well. So there is a bit of a pedagogical purpose to that. There isn't
it helps me too because I don't know much about machine learning. So, but I can understand everything you've talked about so far. So this is great. And I would classify myself as a machine learning beginner. So hopefully this is helping the other folks that aren't necessarily that familiar with it as well.
Exactly, and I think that is a great point. Height, width. Sorry, I'm also. My typing and talking at the same time have
single-threaded
a little bit. Yeah,
I'm the same way. I can't type and I can't really do much of any two things at one time.
Understandable, honestly. All right, so we've now refunctioned this so that we now have a global height, width, and or channel. Some of you may note that it would be actually more convenient for me to just initialize it here in this like in kind of the init part of it, and then use that. I'm using global variables because I'm lazy. I would actually recommend having this be like a auto-configured version, which it is now, where like if you hand it some uniform size set of images, this will adjust its sizing accordingly. But global variables are generally not a great practice. Now, there is a reason for that, which is that if someone then imports this as a module, they then have a bunch of random global variables that are floating around, and they're not sure why, or they might accidentally mess up naming and screw things up. So there's like things and reasons why you might not want to do that. Generally, I would recommend having like a self.like image shape or something, and this is just a tuple with like height, width, and channel.
You could load that, from like a config, like you said.
Right, and that would be a better practice.
Or generate it from the input size.
Exactly, and actually, since that is kind of a substantially better practice, we're gonna do this equals 0, or actually we'll set it for the MNIST data set. So we've now given our Kmeans classifier a couple of extra parameters. I'm going to then not use this, and our preprocess step is actually also going to return to us the parameters sizes of the data. And so this will return to us an HWC version of the data, so it returns the shape.
Magic number is my favorite type.
Yes, magic numbers. Well, I mean, so this has a meaning to its magic, but this is also just by default. So you can override those defaults at will. But yes, they are magic numbers, to be clear. I think they're a reasonable default because it's a common training step, but that's okay.
This is a new high. Nick following good coding practices. So it's bad.
That's funny. Equals H, width equals W, channel equals channel. And some of you may be asking, why would you not just do that standardly? And that's a great question. We'll answer that.
It takes energy. It takes time and energy.
Yeah, it's like, well, I could have, I got the tuple as a return. I could have returned the tuple and passed it in, but we're not doing that. All right, so there's that. Let me just make sure that I'm not running any code that I don't really feel like running. We're not going to fit our data yet. I just want to make sure that that didn't break everything. Not enough values to unpack. Of course there's not. Oh, well, okay, that makes perfect sense. And since you guys are very quick at spotting errors, I'm positive someone has already said this in the chat, but that's okay. We're gonna, there you Yeah, there we go. Cool. So now I have those parameters. They get passed back to me very functional style from preprocess. And that's even not probably the best place to pass it back. It would actually probably make more sense to put it in load data. It's a great point. So that's OK. We'll figure it out. But I might rearrange that before I throw this on the GitHub. But for time's sake, this works, and we'll move on. So we now have an image shape, which is a little bit cleaner way of designing this. That way we don't have to have this global height, width, and channel. And then we just want to replace that with self.imageShape. There you go. Which is beautiful. And now we should be able to display our means even after the initial kind of randomized distribution. So we're going to uncomment each of these now. Now the display means on its own is actually going to take care of this for us, so we're not going to have that there. And we'll do this. And it hangs, which is perfect, because that means we have images here.
Oh, man.
Wow, we look lovely. So here's cluster 1. You'll notice that you're kind of
I'm in a couple of
ephemerally?
Ethereal,
here?
ephemeral.
Yeah. We're kind of in like a dreamlike state. You see LF Python is like hardcore just sticking out right
Yeah.
And then there's like a produce over here. Oh, and we're freaking out every time I touch the image. I'm not going to touch the image anymore. And if we go to cluster 2, it's not a whole lot better. I think I have about 4,000 different pairs of eyes.
Yeah.
Your hair is...
I guess you can see my face
your
just a little bit to the
too.
left.
Yeah.
Just a little bit to the left. You see my face just kind of looking in like a ghost.
Yeah, exactly. So you're kind of just like, hey. It's almost like if you ever see those images, or movies where someone like moves really quickly and you can't focus on them.
Or like someone's tripping hard on some LSD and people are moving around.
So these are our randomized
drunk simulator, Duncan says.
Drunk simulator. Yeah, if you're seeing this, you might want to go see a doctor. Like, seriously. So those are our two images, or our two clusters, sorry. Now, you'll notice that we actually have, by default, 4 clusters. So I can change my initialization to 4. And when we go back over here, we get some kind of interesting results. It is still scrambled, but there is a little bit sharper definition to each of us.
Yeah.
You'll notice this.
I have glasses still.
Exactly. Now, this one's all over the place. So there's that. So Adamantine bipartite in the chat says, it looks normal to me. Doesn't everyone see like that? And I hate to break it to you. You may wish to go see a doctor. And then we can kind of scroll through here. My smile is very defined. And then you're over here.
Yeah. And whatever that monstrosity is on the right.
I always love doing it. It's very entertaining because they just
this is just from one mean calculation though, right? This isn't. This
is just random. They just threw a bunch of random images in there and calculated the mean image, and this.
So we have to like keep doing this over and over again to actually get.
Something we have to do the fitting step, which will make this a little bit less horrifying.
Yeah. We haven't actually.
We've actually not fit anything.
Oh, okay, gotcha.
Which is really entertaining.
We calculated the mean, but we haven't actually like reassigned and then done the mean.
No
reassigned, done the mean.
So for I in range, people are going to shout at me to use xrange. Sorry. And we're going to just have.
Are you using Python 3?
We are. So actually, xrange wouldn't work here.
Range is xrange.
Yeah, range is good. We're chilling. I always forget which Python I'm using.
Python 2 is xrange. Yeah.
Yes. Yeah. So we now have this like. Iterations.
That's cool, like a red comment.
Don't hard code.
What extension is that that does the comment coloring?
That's a great question. I think it's prettier comments.
Okay.
Let me see. Oh, better comments.
Nice. Right. I like that. I might investigate that.
Yeah. There's a lot of really cool extensions for VSC, and I just hadn't had the time to really like sit down and do stuff. I didn't have the time this weekend either, but I did anyway, and it's really nice. I'm a huge fan. I mean, you can make your own custom like colors and comments and things, so I'm sure I will do that, and I will showcase them here probably a lot. But for now, I just have a couple. I have a handful, and I really like using them. So yeah, there's that one. I think I also have a one in red that's like to do. Oh, sorry, this is orange? Question mark? Yeah, and there's all these different like color combinations for comments. They support a ton of languages. We're advertising all sorts of things here as an FYI. Okay, so we have for I in range 2. I told myself don't hard code it, but you know, we'll figure it out later. And essentially what we want to do here is we want that kind of iterative step. So now what we're going to do is iterate over the data and find which cluster each image is closest to. Then assign to that cluster. And each cluster, we'll say new clusters, is actually just going to be a list, an empty list for I. Actually, it doesn't matter what this is called. Right. Oh, and you guys, I think the standard pet doesn't use those anymore. All right. So essentially, we create some new clusters. We initialize this just to be empty lists. And this is where we're really non-performant, but it demonstrates very clearly the algorithm that we're doing. And we only have 40 images. It's not too bad. If you wanted to do this a lot more performantly, you would recognize that you can actually just kind of label which cluster they should have been and then use operations to calculate the new means without moving everything. Sorry, I watched the chat. Adamantium by Apartheid says, Bavignite, it's too late for that. You've already insulted him. That's me. The praise means nothing now. Don't worry, Bavignite. You've not insulted me. I appreciate it, but you're all good. Everyone's good. I do like to customize stuff. I'm positive you have that kind of talent. I really like to feel at home with the things I build. So that's why. Yeah, I don't think we've ever encountered a bad. No, this is not a challenge. We've never encountered a bad-natured comment in these streams. I think everyone's pretty friendly and kind, so we appreciate that. All right, so I'll comment this. Initialize new clusters. So now we're going to iterate over the data, and every time we, that is not a challenge. So every time we find a given image, we're going to calculate using some distance parameter, or sorry, distance function, the difference between it and the cluster that we're currently looking at. Oh man, yeah, okay. Well, it was a good effort. So
you know what you were getting into.
I
when
know.
you said
I
it.
really should have kept my mouth shut.
Can you just do a list literal instead of saying a list, the list constructor there, by the way, or does that cause a bug?
Oh, you can. Yeah, so you can very reasonably do this. I just prefer the list constructor in the sense that instead of doing this, I prefer dict or set.
Do you really?
Yeah, well, because if you do an initializer like this, I don't necessarily know if you mean an empty dict or an empty set.
Oh, well, for that makes sense.
Yep. And then because of that, I ended up getting into list constructor.
Well, actually, does an empty set literal behave as an empty dict literal?
I believe so, yeah.
Really?
Don't quote me on that. I know I said that.
Because I think
Merlin says there is no empty set literal.
Yeah, because I was gonna say I usually only see the set constructor.
Yeah, that's a good point. And then you would just have a set constructor that works for blah.
Well, in that case, it wouldn't work. You'd have to say set something equals that.
Yeah. Yeah, well, that's a good point. So I guess I just use the constructor because it clarifies to me on quick reading.
Gotcha.
And maybe it's just a bad habit that I've gotten into. So good point.
Different strokes for different folks, man.
Yeah, that's a good point. But yeah, you could flip out or swap out that one and it would work just fine. All right, so then we say for image in data, everything that I want to do is I want to check how close it is. So I want to get a list of the distances. So I'm going to call this distances. And I want a list of the distances from this image to each of the clusters. And so we're going to do that in cluster order. And we're going to say self.distance of image and cluster. We'll say cluster mean for. Oh man, this might not work super cleanly as a list comprehension. It's a little long.
I like to use them whenever possible, but they get a little bloated.
They're a little out there.
Well, also you're zoomed in too, which to make it readable for the chat.
So actually, this
it's kind of hard to do.
I guess is a little bit of a mess, but that's okay. And this does what we want it to do. So sorry. Hopefully it's easy to read for everybody. My text wrapper wrapped it around. Hopefully it's not too big of a pain. If it is, you can download the code after, and it'll be a little bit clearer to read.
Where's the distance function?
Yeah, great next question. We haven't defined it. So we do need a distance function. We have our fit function. We have all these other functions. We do need to find
Part of me is worried that I'm not following along with what you're doing, and then I realize that you're writing just functions that don't exist.
We're writing things that we just imagine exist, and they do certain things that we think exist, but they don't actually do anything. Or at least they don't
this
exist
is going to calculate the geometric, the distance formula for our image, our mean of our image versus or whatever current image we're sampling versus the mean image in that cluster.
Yep, exactly. Okay. And so this is going to take in two NumPy arrays.
I always forget this formula too. It's like x2 minus x1, like the square root of all of that.
Actually, we're just going to call it image 1, image 2, because that's the general version of this. And all we have to do is return a single number. Now you'll notice that I kind of went away from my way of documenting these down below. Sorry. If I have time, I'll clean it up. welcome to coding. So just laziness. All right, so we'll break this function apart, even though you could condense it into one kind of ugly line. It's actually not terrible. So what we're going to say is like deltas is equivalent to really just image1 minus image2. It's not too bad. Then squares equals deltas squared. And then sums. OK, maybe I should have just put this all in one. I don't know. I think this is useful. And then the distance is equivalent to np.square root of sums. And so what we then do is just return distance. And yes, you can combine many of these fairly reasonably into one, but we're not going to in this case. So first, I look at the difference between each of the coordinates within the image. So if I'm at like pixel number 79, I subtract it from the corresponding pixel number 79, and then I call that delta for difference. And then from there, I take all of those deltas and I square them. So now they're all positive distances, or distances. This is just kind of like the standard Euclidean way of measuring the difference between 2 points.
Because you
or
can
two
obviously
sets
have
of
a negative
coordinates.
distance.
Right, it's not meaningful in our context, so we're not going to use them. So we square everything, and then I calculate the sum of each of those squares. So I'm just adding up each of those kind of like individual point-wise distances, and then the distance is the square root to kind of compensate for the fact that I had this square term here. Now you'll notice mathematically that's not exactly what it does, but it kind of roughly puts us back down into like a normal difference. And so now distance will tell us what the distance defined by us between two images is. Now there are other metrics for distance. So maybe let's say I wanted to do like the minimum distance between two things. Then I might actually just take the minimum of deltas, for example, where each pixel has some distance, and then I take the minimum distance between any two pixels. Except what I would actually have to do is calculate this deltas for all pairs of pixels. So like pixel 0 has some set of distances from all the other pixels, and then pixel 1 has some set of pixel differences from all the other pixels. So it's a little bit more computationally intense, but either way, you're performing some computation. And what this lets us do, the reason we abstract out this distance function is, of course, to allow us to swap out distances pretty conveniently. And there are many, many versions of distance functions.
Yeah, Bavik Knight recommended Manhattan distance, but I have no idea what that means.
Not super familiar with it, but there are many. So we now have a way of getting the distance. And if you look down here in our kind of iterative step, we're iterating over each image within our data. Let's just verify we have data. Yeah, cool. And what we're doing from there is we're saying, OK, how far are you from the cluster mean for each cluster? And then the one that we want to assign it to
is the least one.
The minimum one. So we're going to do np.argmin of distances. And this tells me which index has the smallest distance. Oh, cool. So Manhattan is actually just the L1 distance. And Euclidean is L2. You can go all the way through L infinite. And
I don't know. What is L? What does that mean?
Not sure where L came from. It's really just kind of like a kind of standard, unlike the Wikipedia page, is like L1 space, L2 space, and so on, L infinite space. I believe the L1 space is kind of like a unit square. L2 is like the circle, and then L infinite, oh, sorry, maybe L infinite is the square. L1 is this like diamond shape, and then L2 is our circle for a unit.
Yeah, I'm gonna have to look that up at a later.
It's something. I mean, it's kind of worth looking through, but it's not super important for us. We're just going to use L2/Euclidean distance.
Bad Bayesian. The name sounds fairly mathematical.
Yeah, Bayesian is very very entertaining. All right, so we now know which index we're going to assign this this image to, and we're going to just say new clusters. At index.append image. And people are like, wait, but you have horrifyingly like created new things every time, and it's ugly and gross. And you're right. I'm sorry. So we now create new pieces every time, and it's not super performant and things, but
Are we then reassigning new clusters to the mean clusters in the class?
Yeah, so then after all of these images have been reassigned, we're then going to recalculate our mean. And so now what we want to do is just kind of copy this.
Adam, I think I did check out that website at one point, and it looked like it had a lot of notes on it. I've been not spending a ton of time on math. I do want to get my math up. I need to get through calculus, which means I'm reviewing pre-cal at the moment, so I'm not exactly as up to the skill level of most Harvard grads or Harvard undergrads, but it looked okay. I haven't spent a lot of time on the website, but thank you for the suggestion.
Huh, sweet. Yeah. And more math, tends to get a little bit easier to do a lot of things, actually.
It's cool
it's pretty important.
Hated math growing up, but I get more appreciation for it the more I see it in the context of CS.
Yeah,
which
exactly.
I care about more.
Which is a good point. So essentially, this is it. We've now fitted our data.
Right.
So
what
this
is going to happen
here,
twice, or two?
Yeah,
it's going to fit twice.
Now. It'll fit over 2 iterations. And actually, we'll just do it once, just to see what it looks like after only 1 iteration.
Okay.
And actually, let's make that a parameter for fit. Is iters equals 1 by default. And then we'll just have this be iters. And that way I can control it using the command line, or not the command line, but other things. And essentially what this does, now just to recap for everybody, we did say that we were going to repeat what we were doing over and over again. So you will hear it many times, and have heard it several times. So we initialize some set of new clusters. Every time we want to go over some iteration, it's just a bunch of empty lists. And then what we do is we say, OK, now we iterate over every image in our data set. We calculate the distance between that image and every other or all clusters using our self-defined distance function. From there, we know which index we should reassign it to, or which cluster we should assign it to, by taking the argmin of those distances. So just which argument provides the minimum of distance. So if I iterate over distances and the minimum number sits at index number 3, argmin will return 3. It does not return the minimum distance. And then our new clusters index is going to, at that index, we're going to just append that individual image. And then from there, after we've kind of iterated over all of the data, we're going to say, OK, now recalculate the mean given our new clusters. And then we're going to iterate and just do that over and over again.
So this is going to garbage collect the prior mean images.
It will garbage collect it. I could delete it in certain ways and build this a little bit better. But we're being kind of clumsy for the sake of education.
Luigi actually made an appearance in today's stream. Hello, Luigi.
Hey,
good to see you. Luigi's a longtime CS50 follower on the Facebook, and we've met in person in the UK.
Wow.
So it was pretty cool.
Oh, that's wild. Oh, that's crazy. That's awesome. Well, thank you for joining us. And so we now have our fit function, and we have the ability to display our means after we've done it. So now we just got to put everything together.
Cool.
And so we're saying that k equals 4. We're going to try and run fit once. So it'll only run through 1 iteration. Oh, and I did want to pretty display this, as people might have pointed, or no one really pointed this out, but we're going to do it anyway, because it makes things really user-friendly. TQDM. Yeah, there we go. So adding those 2 very simple tags to the developers of TQDM's benefit, it allows us to have this pretty iteration. So you'll notice after we go through all 40 of them, our little progress bar filled up. And if we had many of these steps, this would make things a little bit more convenient.
It's pretty cool. Oh, wow. It's starting to look
and it's looking a little bit cleaner,
coherent,
right?
Yeah.
And this is after only 1 step. We haven't really done anything. But the image for cluster 1 is actually fairly reasonable. We look a little bit more like people. This one still has my face kind of ghosting in the background, but it does look a little bit more solid. We seem to have some kind of steps taken to make us all look
I got crazy tan and then harsh fall off there to much paler.
Colton actually bathed under a torn piece of aluminum foil.
Yeah, that's what it looks like.
Sunbathed, sorry. And in this one, I look like I might be a multidimensional being, but we are mostly in the right realm. And then Colton also looks like a multidimensional being who's, again, mostly in the right place.
In and out of existence.
You're mostly in the right universe. And then here we have, wow, Colton's pensive look is very clear in that one, whereas mine is just I'm all over the place. But we are seeing some clarity. So now let's run it, I don't know, 10 times or so. Okay, that was ugly. We're going to run that around 10 times and see what happens. And we're going to just fit with iters is equivalent to 10.
I'm very curious.
And we'll see what ends up happening here.
It's probably going to take a while. Oh, I'd say it doesn't take that long.
So not too fast, or sorry, not too slow. Now, this looks pretty clear.
It's more clear.
Of course, there is some kind of natural variance as Colton runs around. And as you can tell, I move around a lot when I talk, and Colton moves a little less when he talks, because his image is a little bit more centered on him, and I'm all over the place. And we didn't normalize these for making sure their faces were in the same place or anything. We just kind of let it go.
Interdimensional photograph. Yeah, that's pretty accurate.
It really does. And then if we kind of move here, this isn't terrible at all.
I look like I'm looking left and right.
which makes perfect sense, because some of those images have you looking at me, some of them at the screen. It makes actually a lot of sense. And you can kind of see a faint outline of my arm from one image.
Oh, true.
Yeah. And my hands come up all the time and things like that. And then from here, this again looks like it's about one stream, which is not terrible.
Okay.
And from here, we also have, again, about one stream.
So what if we did it 100? Because it ran pretty fast.
Right, so we'll kind of let it skim through them. You will, and actually, to kind of quantify what's going on here, we're going to calculate kind of the overall average distance of each image from its respective cluster. And so we basically want to see, at each iteration, what is the distance of that image from its current cluster, or actually, there's a number of ways of calculating this. We're going to do kind of a ad hoc method for doing this. So for each image, we're also going to calculate its distance from whichever cluster it is closest to. So we're going to do this argmin distances, and then we're going to say the min distance is equivalent to just np.min of distances. And we're going to use this as a measure of the distance it will be from the next cluster it gets assigned to. And what we're going to do is we're actually going to just take that and compute an average minimum distance across. So sum min distances equals 0. And so on each iteration, we'll have a version of this. And then we're going to just sum min distances plus equals. And then after that iteration, we will sum min distances divide equals, what was I going to divide that by? Oh, length of data. And, well, actually, what we can just do is calculate. I'm going to do this. Sorry. We're messing around a little bit. And this gives us a way to kind of numerically quantify how bad we're doing. So the higher this number is, the worse off. We're not normalizing against anything. We're not doing anything fancy. It's just a simple average minimum distance across all of the images we have. And I'm not going to print this, but I am going to store it in kind of a self.average distances equals some list. Sorry, no default constructor there. And we're just going to self.averageDistances.append that. There's my corresponding parenthesis. And so essentially, after each iteration, we will add the average distances of the images to this array. And then we can display that in kind of a similar way we did here. Define display averages. We got some weird notation going on. And we're going to essentially follow this format where we're going to just do a plot.figure. And then we will do a plot.scatter. No, we don't want to do scatter. Plot.plot. There we go.
The classic.
Classic. Average distances. And then plot.show. And we'll do plot.title. Average distances over iterations, and plot.x label iteration number and average distance. And this allows us to then show, after everything has gone through, what it actually looks like. And so what we'll do here is we'll copy that notation, .display averages displays the average distances over iterations. And Kmeans.display averages. Cool. OK. So hopefully everybody followed. There's no way. And that's not necessarily us bragging or anything. That was kind of a messy walk through a quick build of a function. But essentially what Colton was asking me was, can we run this 100 times and let's see how it kind of goes? And yes, we can run it 100 times, but what we'll end up seeing, hopefully, knock on wood, is that the kind of loss or error that we have, and this isn't necessarily a great measure of loss, but it works in this case, will go down exponentially like this. And so after I think around 10 iterations, might even be fewer because our data's so small, we actually won't see a whole lot of improvement from there on. And so now if we run this, oh, I didn't run it with 100, sorry. Let me run this with 100 iterations. And we'll watch that ping through for a sec. And now as that's pinging through, I'm actually going to add a try.
You're going to try and do a little bit of
we'll do a little bit of error
engineering.
Handling. And this way we have a little bit cleaner exiting if I decide to cut it off in the middle. Now we ran over 100 iterations, and we will see that things got pretty clean.
It still about the same though.
But yeah, it's not a huge difference, right?
Yeah,
and so everything's pretty much as clean as it can get, in that these images, the average is that within a stream, I took a series of photos, and those kind of screenshots or photos, in each of those frames, we're actually not doing the same exact thing. You know, like I'm kind of moving around, I have my hands raised or whatever. And because of that, you'll see that our kind of average distance, at the very beginning, after 0 iterations, it's enormous. We have this kind of, it's high. But once we drop down to like around the first iteration, we hit pretty low. And then we achieve our lowest after only 5 iterations, give or take. So we really don't need too many iterations in order to get the images that you saw there. After that, it's actually probably just assigning the same images over and over again. And so you'll notice if we do like 10 or so, now that we have kind of a quantifiable metric for this, once it goes through, we actually have exactly that. Oh, sorry. So after exactly 2 iterations, we achieve our minimum distance, and it's basically telling us that it has classified everything as correctly as it can possibly get.
Interesting.
And so this extra bit, where we're at like 100 instead of a 0 distance, is really just kind of due to the variance within each cluster. Now, speaking of variance and a little bit of statistics, let's do a normalizing step to kind of clear things up a little bit. So in our, I'm going to keep collapsing these so I can read them. In our pre-processing step, we flattened things, and I mentioned that maybe in the middle here might be a good time to normalize our data. And what that is going to mean for us, and it does help Kmeans a little bit, although in our case our data set's pretty simple, is we're going to subtract out the mean and then divide by the standard deviation. And that'll give us a standard normal distribution, roughly. Well, what it'll really do is it'll set our mean to 0, and it'll set our standard deviation to 1. And so we're going to do that. We're going to get the image mean, which is actually just np.mean of flattened axis is again equal to 0. And then we're going to get the image std, which is np. I believe std, yeah, of flattened axis again equals 0. And we can say normalized is actually equal to flattened minus image mean divided by image standard deviation. And now, instead of swapping new data for flattened, we're actually going to just call that the normalized version. And so essentially what we've done here is we've converted everything into the normalized versions of what they are. And we're going to see how that kind of changes what our means look like. So we go through here. Oh, yeah, OK. Well, sorry. We do have invalid scalars. So in this value, we did have some kind of like invalid conversions as far as numbers go because of the way that we normalized that. So let's go ahead and double check that we're doing things correctly. The standard operations should work across matrices here. I have a feeling it's because everything has not been normalized by like pixel value. That wouldn't make sense. Oh, some of the standard deviations of pixels are 0. Yeah, so what we could do is replace every standard, like in the standard deviation, there are some like numbers that are 0. You could fix that by just swapping them out with like 1 or not dividing by them. There's essentially we divided by non-numbers, or we created non-numbers. So this is like, or I guess this is actually bang semi-normalized. This has the right mean, it has the wrong standard deviation, which is not going to help me prove my point a whole lot, but that's OK. So we run through 10 of these. Oh, right, and it has to be the right range of numbers. So when we divided everything out, in order to get it to be back in the right valid range for imshow, which is what this error is saying, it's going to flip it to the correct parameter set, basically from 0 to 1 if we have floats, or 0 to 255 if we have integers in our pixels. And you can actually see, I think if you do normalized.dtype, possibly, and print that out. That's hacky. Well, that's okay. It's floats. But if you were to then print out like a small sampling of normalized and look at kind of the ranges of those values, you end up with these weird like negative values and so on, which is not quite what we want. So essentially what you'd end up wanting to do is actually kind of either unnormalize them, or before you go to like try and image show them, you should actually convert it back to the proper range, which is not particularly difficult, but we may actually be out of time to do that. So I'll leave the normalization code in there to be adjusted later. And then we'll spend the rest of our time actually talking about what this would have done instead of continuing to do it. Just because it is important, but we're gonna leave it alone for a sec. Because I think it's not super important to what we're actually doing. So what we were going to do there, and what we really will end up doing eventually, is normalizing the data makes it a little bit easier for Kmeans to not be as, I guess, responsive to random variance within your data. And so as Colton pointed out, we do kind of look like we're from like a new century or so every time we display these. And the reasoning for that is essentially that within our data set for each cluster, I've done all sorts of messy things now. Within our data for each cluster, we have essentially ended up creating these kinds of like allowing for the variance. I mean, it's a mean image, right? So it's kind of just a representative image for each stream. And you'll notice that when we did create it, I've made a small mistake somewhere. It actually ends up working out okay as far as like what we want it to be, which is to have each cluster representative of one stream. I do seem to have a issue now in my functions, but it shouldn't be a problem here. So we're going to just verify that we have working code before we leave you guys, because that would be rough. I don't see why that's a problem. Oh, OK. I guess those were problems. That's strange. Whatever. OK, so essentially what you can see here is like things that didn't change at all. Wow, I can really not touch that. Such as kind of the background of the image are going to be pretty consistent. There was almost no variance in those pixels. And so when I said, oh, we want to normalize this by subtracting the mean and dividing by the variance, well, a lot of those pixels, for example, have 0 variance. They don't change at all. And in fact, in all of our streams, this like upper corner is probably always white. It's literally always the same pixel. And I think that's pretty much always true, which means that the variance is 0. And if I try to divide by 0, I end up with not a number. When I try to print that not a number, it freaks out. So we can't quite do that. There's a little bit of an extra step that we would need to take there.
Yeah, Bevan was saying use a try.
Yeah, so as Anant points out, variance cannot be 0. That's a great point. It has to be always positive. My intent basically in saying that is that actually, yeah, they shouldn't have any variance in this case. So actually, I do believe variance can be 0. I'll double check that so that I don't say anything crazy. Can be 0. Question mark. Yeah, so actually it is 0 in this case, and the standard deviation is also 0. A variance or standard deviation of like 1 would be like what you see in like standard normal, but in this case it is actually 0. And that's just because the pixels don't change at all. Variance cannot be negative, as an FYI. From there, what we would have normally seen is kind of a ugly-looking version of these images.
They're arguably already there.
They're already kind of there, but it would have given our Kmeans classifier a little bit easier time doing this classification, which we could have then shown with this next figure, which shows the kind of average distance over iterations. I don't think we could get a whole lot faster than just in 2 iterations we're there, but that's OK.
Just some really talented programming, right?
Yeah, you know, that's just it's a result of the careful selection of data set, question mark. So if we were to extend our data set to something like the MNIST data set, then you end up seeing this actually perform a little bit more real world like. And even then, they've done a lot of normalization for you. Also, your data is all binary and it's in the right format and everything. So there's a lot of stuff where, like in the real world, you would have to do a lot of pre-processing yourself generally. But some of our pre-processing steps, which we should take, are to like normalize our data. We should extend our data. So like flipping us2 should actually still be part of the same stream. Like if I swap the literal image around, that's still part of the same stream. If I include black and white images that are represented under a color scheme, but they like visually are constructed to be black and white, those are also part of the same stream, and so on. And we as human beings can deduce that, so I want the machine to be able to do that. And that's just kind of like an image augmentation step or data set augmentation. So there are many other like steps and things that we would take there. But the main part that we wanted to get to by the end of this stream was, well, but what if I gave you a data set, I had you train your model on it, and I want you to build a new image that would have fit within that data set? And that is where we're going to kind of leave you guys today, actually, is so we've built this classifier. It lets us divide everything into these beautiful clusters, and they are all representative of some class that we have defined has meaning. But I also want to be able to, what was I going to say? Generate new images. And if I wanted to do that, then we might use something like a recurrent neural net, or in this case, it's actually a CNN. And so what we do here, and I actually pre-ran this because it takes a lot longer to run. And in this case, this actually is from the MNIST dataset. And now this doesn't look particularly beautiful. It's actually pretty hard to read, but if we go all the way down, yeah, it really does. And if we go down here, this is the sample that was generated using only 50 training epochs and kind of on my own CPU, and very simple. And this is kind of where we're headed next week, except it'll be with Colton and I instead of the MNIST data set.
Those are hand-drawn digits, right?
Yeah, sorry, it's the hand-drawn 0 through 9 digits. And they've been normalized in many ways and kind of formatted prettily. They're also very small. It's 28 by 28 pixels.
Right. Ours are like 600 by 200 pixels.
Ours are pretty massive, although we were actually still able to get through very many of them very quickly.
Yeah.
Because NumPy is pretty powerful.
Sprites for a sci-fi game, that makes sense.
They really do kind of look like them. You'll notice that some of them do have clarity. So like this 4. There's, I think, a 7 here. It's clearly a 2 there, like a 5 here, maybe like a 0 and a 1. And essentially what this did was the program is actually, this code is not mine. I borrowed it just for the sake of having something to show you guys. It's called PixelRNN. The link to that code, oh, thank you. The link to that code, if you wanted to do like a generative version of what we were designing today, is here. And that's just from this guy, Phil Cuz, or at least that's his GitHub username, or their GitHub username. And they built a really cool article that demonstrates how like pixel RNNs are really slow and computationally intensive, but you can retain a lot of key features and points by using a CNN, a convolutional neural net. And then he provides some code. I cleaned up some of it and modified it to fit what I wanted it to fit. But yeah, you can essentially go there if you'd like and try and figure out how to use their code. And it's not particularly difficult. It's pretty well built, at least in my humble opinion. And it lets you kind of play around with the MNIST data. What we're going to be doing next week is kind of building our own version of this from scratch, kind of like we did today, with convolutional neural net, actually. So we will be building, using TensorFlow, a full-on convolutional neural net for you guys to play around with. And yes, this will go on a GitHub repo. Let me put that up right now, actually.
So yeah, today was Kmeans Clustering. So next week, Wednesday, do you know? We can't do Monday, Tuesday anymore.
I'm not sure, probably. Yeah, I think Wednesday would probably be okay.
Okay.
I'll have to double check on that.
We'll confirm that. So today was part 1 of what will be probably a 2 or 3, maybe 4-part stream on neural networks and machine learning. But this is fascinating. I really enjoyed this. And it's actually pretty simple. Like the idea of what a K-means clustering algorithm is not terribly complex. I trust that it will get more complex as we dive into the actual neural
nets are pretty complex
side of things. So yeah, stick around for that. Next week we'll talk about convolutional neural networks, as you said.
Yes.
Generating stream images.
Generating images.
From the same data set that you just saw, and that'll be fascinating. I can't wait to see that. We'll put a GitHub link. Actually, well, if you're going to create it right now, I can just plug the link in the chat, actually.
So that is the link, HTTPS GitHub powerhouse the cell. Oh, sorry, that's really small.
GitHub.com/powerhouse.
That should be much more readable.
The cell. Kmeans. That should work. Just Kmeans, right?
Yep.
Okay. Cool. So that's today's code that we wrote here, right?
Yep.
Okay.
Yeah, that is everything you saw today.
What was the other link to the other person's CNN or RNN?
Oh, right. I will throw that up there in one moment. Also, pointing out, add is not a great add dot is not a great practice, but
I do it. Yeah, I do it all the time.
Oh, also, hopefully you're okay with your images being displayed to the public.
Yes, I am.
I have also
you haven't spoken. You have spoken consent. Yeah. People are saying that your typing wasn't too bad today.
Oh, thank you. Yeah, it has improved a little bit. I think it's because I don't know. I think I was just paying attention. Like, I think I wasn't talking quite as much. I don't know. I have no real explanation. Maybe I'm just less sleepy. I don't know. I have no real reasoning for that. All right, so their GitHub is here. The article that they used is the first link I have
Phil Cuz.
Yeah.
And it's pixelrnn.git.
Yep. RNN caps.
Cool, so check that out. And what was the article?
And the article is also up there. Oh, well.
Is there a link to the article on the GitHub repo?
I believe there is. Okay. So you should be able, and I mean, you could also just type in Philip, I'm not going to pronounce that. Kuznetsov. Yep. Cool guy. This is a really cool article. It's pretty easy to walk through. It doesn't require too much math. And you can kind of understand why this kind of CNN has some advantages over an RNN, at least for like playing around. But yeah, I would recommend kind of reading through that article. We'll talk through a lot of the same things that he talks through in his article. We're going to probably spend a lot of time dealing with like what a convolution is, because that is something from like signals theory and processing. But it is very useful to understand what they are. We will build probably a convolutional neural net because we'll want to demonstrate it in the stream. There will actually probably be a bit of template code that we'll put up just to make it a little easier for the people at home to follow along. We'll build some helper functions to make things a little simpler. And we'll put that all up on GitHub. So yeah, thank you for listening to the Kmeans image vomit, I guess, that came at you guys today.
No, this is good. This is good stuff. Someone asked, what is chat codes Python? So nice segue to tomorrow's stream. Just going to be me tomorrow. I'm going to basically have chat open, and we're going to write some Python scripts. But I'm not going to write any of the lines myself. People in the chat are going to write the lines. I'm going to sort of call on people, and we'll assemble a Python program line by line based on what people say in the chat. And we'll have, I think what I'll do is I'll bring a few like target exercises to the table, like let's print hello world, like let's create a function that will sum two numbers or something like that. And then what we'll do is we'll mark each individual line with that username of that person so we can see who's contributed to the script all at once. And we're gonna use only icons for people when I call on people. So we can either do gutex in the stream or kappa in the stream, and that'll let me know that I can call on you. And we'll see where it goes. It's an experiment. It's part one of an experiment. Last week we did the same thing with a text adventure where the chat wrote the whole text adventure out, and we sort of assembled it live on camera. So tomorrow's going to be that, but with code. So
sweet.
It'll be interesting. If we don't know Python, can we do int x equals 5? Yeah. No. If I call on you and you give me a line, I'll try and help you fix it. I will try not to put too much of my sort of influence on the script because I want it to fail and succeed at the same time for comedic and educational
entertainment
effect. Yeah. So we'll see how it goes. It'll be interesting. So tune in tomorrow. That's at 12 p.m. Eastern time. And I will be curating all of the lines, so we will not accept
won't accidentally
things
wipe
like,
your own machine.
Yeah, no, we're not letting this sort of be automated. Like I'm actually going to be calling on people, and then we'll be sort of all together writing it and curating it as we go. So we'll see how it goes. Should be fun. I'm very excited. Yeah, eval. No malicious code should be possible unless I'm very susceptible to being duped.
They kind of like do like a hieroglyphic style malicious code. They send you characters you don't know what they mean, and they're like shortcuts in Python.
I would probably be a little bit skeptical of that. So staying within the realm of what I assume to be safe. But
that makes sense.
Plus, it's going to be multiple people typing, so it's like everybody has to get together and have like this conspiracy. It's perfectly executed. Which everyone knows. That's just not.
I think that'll be really fun.
Yeah, I'm excited. That's part one of the experiment. We'll see where that goes. See if people like it. We'll see if we can make it better. Maybe we'll try different languages, but it'll be in Python tomorrow. And yeah, it's just an experiment, just for fun.
Oh, sweet.
Cool. Well, thanks very much for today's stream.
Thank you for having me. As always, I'm always happy to be here.
I now understand what Kmeans Clustering is.
Yeah, now if anyone asks you, like, whoa, Kmeans Clustering, you can be like, I literally watched one get built in front of me.
Yeah.
And you could probably build one yourself. I have high confidence you could figure it out.
I think that sort of seeing this stuff being built from the ground up, it makes it a lot easier to understand. I mean, that's kind of like a self. I think that's like common sense, but...
Yeah, but when you see it on like an online tutorial, all the code's already been there. You don't see the thought process necessarily.
It's nice to see the thought process. Yeah. It's nice to see that. Ciao ragazzi, says Luigi. I don't know what ragazzi means, but I know what ciao. Ciao means bye, or it actually means hello and bye. But
like aloha.
Maybe someone besides Luigi or Luigi himself can clarify that.
Yeah, good point. Yeah.
But yeah, thanks so much. So we'll see you again next week.
Yes, I'll be back next week. I think probably on Wednesday.
Okay. Yeah, we'll touch base and we'll get it figured out. Thanks so much to everybody who's been in the chat today. This was a lot of fun. Our first in probably a sequence of many videos on machine learning.
You will see our faces many, many times in many different ways. I'll be taking more screenshots.
Hopefully in some generative ways. I'm curious to see what the computer thinks we look like.
I'm horrified to think what we're going to
sort
look
of like a hybrid between you and me. That's going to be interesting.
Oh yeah, it'll be a time.
Yeah, it'll be a good time. It'll be a good time. I'm excited.
Yeah, I think it'll be pretty good.
But until then, have a good rest of the evening, depending on where you are. Maybe rest of the day if you're somewhere really far away from Boston. This has been CS50 Live with Neural Nets Part 1. So today we didn't really do anything neural net related.
I guess there was no neural net.
This is the groundwork for it. Kmeans Clustering.
You now know why we wanted a neural net. Yeah, it's been motivated.
I think if we dived right into neural nets, people would be like, "What the heck is going on?"
Yeah, if we hopped right into that, that might be a little much.
Yeah. But no, I'm very excited. This has been great. Thanks again so much for this.
Of course, thank you.
CS50's Nick Wong. My name's Colton and Nick. This is CS50 Live. Enjoy the rest of your day, and we will see you next time. Bye-bye.